Hello everyone, welcome to the beginners track at ZuriHac 2025. I'm very happy that Andreas offered to do the beginners track this year. Andreas is a regular at ZuriHac, but he normally does the advanced track, which I look forward to a lot. Yeah? This year he requested to do the beginners track. Initially I was a little bit disappointed, but I thought that, yeah, beginners also deserve something good. Last time it was, sometimes it was me. So yeah, I'm really happy that you wanted to do this and you are doing this. This is great. Andreas is one of the partners at Well-Typed, yeah? One of the, let's say, most prominent Haskell consultancies. They do a lot of work in the compile tool chain projects in the industry and so on and so on and so on. And so it's really great to have someone like him do the beginners track here. I also think that this is one maybe the largest turnout for the beginners track right now. I counted about 35 to 40 people. That's really great. I also see that there are some students from my functional programming class. I'm going to take that as an insult. Yeah, thank you very much, Andres.
Yeah, thank you very much for the introduction. Yeah. Okay, yeah, so we're slightly delayed. I mean, so one of the things is that, I mean, at Well-Typed, we have a beginner's course, and we haven't actually been teaching it in real life all that often recently. Somehow, since COVID, everything is remote. But it takes, and it's already a compact course, it takes 2 full days, right? And here we have like formally allocated, if you just look at the program slots, we have 4 hours, which is about a quarter of that time. So this is quite ambitious for learning Haskell. But nevertheless, I mean, that's what I'm going to try. I'm going to try to give you a condensed introduction into Haskell, and I'm going to start at the beginning. So I reiterate once again that this is really a beginner's track. It's not something like for Haskellers who have done 3 months of Haskell and want to learn more, but it is a beginner's track. That doesn't mean that if you have used Haskell before, you have to leave the room. No, if you're interested, you should just not have the wrong expectations, right? I'm going to start at the beginning, yeah?
Just one administrative thing, maybe you can say, this room is reserved solely for the beginner's track.
Yeah,
I was
going to get there. Yeah, I mean, so the point is we have these 4-hour lecture kind of thing, which I hope to be interactive as well. So we're going to do today and tomorrow. And then apart from that, if you want to work more on this stuff, and I hope that I've supplied sufficient quantities of exercises and I have some additional pointers as well, you're most welcome to spend the rest of the time working on this as well. It will just not be quite as live. I mean, I might still be dropping by here and then throughout the days. We also have, in principle, 2 TAs, teaching assistants, Matthias, who is there, and Joris, who will probably drop by later, because I already said in the beginning it's not that interesting. Probably most of the questions will be towards the end. But you can ask them, and in particular, if you have any setup, technical, whatever questions that are not about the language, during this, like in the lecture part, ask preferably Matthias. If you have any questions about the language, please ask me, right? Because that's what we're going to do. And I know it's always a little bit weird if we're recorded to ask questions, but the point is you won't really be audible anyway, so you don't have to be overly afraid. I'll just try to summarize your question or repeat your question and then answer it. So you're most welcome to ask. Okay? So the general plan is to not, we can't do an exhaustive introduction. Even just an introduction to Haskell is too large. Haskell is not a minimalistic language, unfortunately. There are lots of different concepts, lots of different ways to do things. But the big goal that I currently have, we might have to deviate from that for today, is to learn how to define data types and functions, right? That's one of the main things. And in particular, we're going to learn how to define functions using pattern matching, which is one of the very peculiar features that Haskell has, which I think is immensely cool, but nobody talks about it very much anymore after a while, because it's just so fundamental and basic. So when people say, oh, why is Haskell great? They never mention pattern matching. They mention other things, right? But pattern matching is actually fantastic, right? And so we're really going to focus on this. Then I hope to convey an idea how you can understand Haskell types. Types play a big role in Haskell, right? So how you can read type signatures, get an intuition for how they work, and we're going to look at some higher order functions. If we actually get through all this today, then tomorrow my plan is to talk about I/O and to talk about a little bit about like using fundamental libraries such as finite maps and possibly quick check and possibly draw some pictures or something like that, right? So that's, but it depends a little bit on how far we're getting today. All right, so I should also say that this is a very, very much cut down version of a full introduction course, which is actually online. So you can go to welltyped.com/intro and then you'll have sort of a full course there, and all the videos for that course are on YouTube in this playlist here as well, but it's also linked from the Welltyped page. And that has additional questions and exercises and so. So it's really, this is not actually using any material from that course, it's just also done by me, and therefore many things will be very similar, but I've really drastically cut it down. And then there are lots of other resources you can in principle use, and I've just put 3 things here, like a course by Brent Yorgi, who's also going to give a talk on Monday, I think, at ZuriHac on Monday morning. I really like Graham Hutton's book. It's a bit theoretical and not so practical, perhaps, but the big advantage of Graham's book is really concise, it's really to the point, it's not a 1,000-page book about Haskell. It's small, it tells you what you really need to know. Yeah, Raphael has it there. That's great. And the relatively new book is Rebecca Skinner's book on effective Haskell, which I also really like because it's a good counterpoint to this one. This one is really trying to like talk from a practical perspective and like solve real problems with Haskell, right? Okay, so much in advance. Let's get started. So I will not actually spend a whole lot of time on motivating the language and why it is how it is. I think this is actually something which we can talk about, but if we want to talk about it, it's actually easier to talk about it tomorrow or something when we've already seen a little bit, right? If I say all those things about how Haskell works in advance, it's a little bit weird because like we're talking without you actually having seen it, okay? If you can't read the comments very well, that's not so bad because I'm going to mostly say what's in the comments here anyway. So this is a file which is in this repository, which you can clone. I mean, if I should have probably said this again, I had this URL up already. So, so there is a repository which has these files. For the part that I'm now going to go through during my lecture, there is actually a branch which has all the code that we're going to write already. So none of that is really a secret. Then there are additional exercises which currently don't have any solutions in the repository. I should probably also say just one sentence or so about AI, right? I mean, these days you are probably used to use LLMs to assist you during coding, which is fine. But I don't think it's a good idea to do it today if you're trying to do these in introductory exercises. There's absolutely no question that most of these exercises can be solved flawlessly using an LLM, right? I mean, they're simple exercises. But you won't learn about the language if you're just doing autocomplete, right? If you actually want to gain your own intuition, you should at least try, right? Okay. So let's start with a simple Haskell file. So this is a Haskell module, right? It starts with a module header. It has a .hs ending, and I've loaded it into my editor, which is NeoVim and has a LSP support, but you can use VS Code or whatnot. And it's actually part of a Haskell package, right? And you can see that because in the same directory, there is also this Cabal file, which is also part of the repository, which gives a little bit of meta information. And yeah, there was a question before about whether I'm going to talk about the tooling. I really don't want to go into this very much, right? I mean, but basically it just gives some metadata, and it says like what other Haskell packages it depends on, which is just one, and it enables all warnings, and it says that there are 2 modules here, and it's a Haskell-specific file format, which Haskell tooling understands. Right. Okay. So let's start. Let's actually say, okay, we just use some example. Let's say we want to model some aspects of a game with playing cards, and we have cards that have one of 4 different colors, and the colors that occur on cards are yellow, red, purple, or black, and then they have a rank, and there are only 3 ranks, 1, 2, or 3. Okay, and we want to model that. So like what we typically do in Haskell, we start by defining our own data types. So it's a very typical thing. So how do we define a data type for colors in Haskell? We write data color, or card color, let's call it card color, because might be that we use other kinds of colors tomorrow, right? And in Haskell, data types, they always have 1 or more shapes. And these shapes have names. And then, depending on the shape, you can have additional fields, like data that is stored within the data type. But in a simple case, such as an enumeration type that we have here, we basically want to define a data type that just has 4 different values. We can just define 4 different shapes, and the shapes have no further arguments, and that's it, right? So we can basically say a card color is either yellow, or it's red, or it's purple, or it's black. Now, data type names and constructor names, these shapes, or these shape names are called data constructors, or just constructors very often. Both data type names and constructor names in Haskell have to start with uppercase letters. Apart from that, you're relatively free to choose whatever name you like, but they have to start with uppercase letters. So that's not an accident that we write card color with a capital C in the beginning, and all these colors have capital letters in the beginning. That is what identifies them as either a data type name or a constructor name. Data constructors are not types. They're values that belong to that type, right? So card color is a type. In my syntax highlighting scheme, types will always be blue, and data constructors will be, what is this? Brown, I don't know, right? Something that used to be yellow, but I don't know. Some other color, right? So you can distinguish. Ideally, you can distinguish by syntax highlighting which of the 2 it is, right? Okay, so now we've defined a data type, and we also want to interact with it, right? So the easiest way to interact with your Haskell program that you're about to write these days, if you have a working Haskell installation, including Haskell language server support, is just using the so-called eval plugin of Haskell language server, which works on comments that then have this triple greater than magic combination. And you can already see that after I typed this, suddenly this what's called a code lens and language server speak appeared, which basically allows me to evaluate that expression. So I can, for example, to do something which actually works, as the very first example, write 2 times 2, and I get 4, right, if I actually evaluate this. But if I try the same with yellow, not yellow times 2, just yellow, nothing else, I'll actually get an error message. As a very brief interlude about tooling, if for whatever reason HLS doesn't work for you, that's a big pity, because it makes a lot of stuff easier, or the eval plugin doesn't work for you. The other way to interact with Haskell code is using GHCi, and the way that you typically invoke GHCi these days, I would say, is using, let me actually start a terminal, is using, this is not ideal. Yeah, sorry for that, but is using Cabal REPL. Oops, no. And Cabal REPL will then load your project into it, and then you can also type Haskell expressions here. So I can, for example, write 2 plus 2, and then you get some warnings. If I write yellow, I'll get the same error message that I got in the editor buffer. So this is a less convenient but still possible way to do this, right? Okay. So yeah, so to work with card colors conveniently, that's basically the step 2 here. It's helpful if we can evaluate expressions and compute colors like yellow is a simple computation which just should evaluate to the color yellow. And then we would want to print the results to the screen. But by default, Haskell doesn't actually know how to print a value to the screen. And that's why this error message here arises. So we have to explain to GHC what string we would want to associate with each of these 4 possible values. And that's very simple. So we can just write our first function to do this. We can call it show color. And that takes a card color to a string. And this is what's called a type signature in Haskell. So this colon is always an indication for something is defined to have a particular type. Right, so show color is the name of the function we're going to define, and it is going to be a function from card color to an already existing type that is called string. Okay, and how do we define functions? By pattern matching. So this is where this big principle of pattern matching comes in. Constructors, even though they're called constructors as if they are going to construct things, they can actually also be used to tell things apart. Right? Because every value belongs to one of the possible shapes for a data type. So if you evaluate it far enough, the compiler can see that it actually belongs to one of these constructors. And you can then match on the different constructors that a data type have in order to say, like, I want to do this if it's this constructor and that if it's that constructor. And you do that just by defining multiple cases. So we define a case for yellow, and we define a case for red, and we define a case for purple, and we define a case for black. And I put underscores on the right-hand side because this is a really helpful feature that Haskell has, that it allows you to leave parts of your program temporarily undefined. Right? It's a so-called hole, and a hole is an error, but it's a helpful error, right? And one of the things that I would like you to take away from learning Haskell is that the type system is your friend, right? It's not your enemy. You don't have to fight the compiler very long until you finally get your program accepted, or that's at least not the viewpoint you should have. You should see basically the act of programming as some sort of conversation between yourself and the compiler or the development environment, where the compiler is trying to assist you, right? And the types are a big part of this assistance, right? Because if the situation becomes more complicated, the programs become more complicated, it's not always obvious what goes where, and if you're unsure, you can put a hole there, and then the compiler will give you additional information. So now in this particular case, the only piece of information you're actually getting is that each of these 4 things has to be a string, right? Because that's the result type of the function that we've already written here. But in more future cases, we'll see that this can be more informative than that, right? Now we can basically say, we want to use the string yellow and the string red and the string purple and the string black for each of these, and that completes the function definition. And now it's ready. Okay, so now we can actually we can still not write yellow. We'll still get the same error, but we can write show color yellow. And that's an invocation of a function to an argument. And this is probably the single biggest syntactic pitfall of Haskell for people who are coming from other programming languages, is that function call syntax is just writing the function with its argument and a space in between. There are no parentheses involved. It's unidiomatic to use parentheses, right? So you can write this, or even without a space, but it will immediately identify you as somebody who is new to Haskell, right? So, right. So this is not what you should be doing, right? Parentheses are being used for grouping. So in most cases, you're going to say, oh well, if this whole expression is an argument to something else, you might want to surround it with parentheses so that it's clear that it is applied as a whole to something else, right? But so that parentheses still occur, but in the simple function application case, they don't occur, right? So you can just write these things right next to each other. Now, we can actually make it an instance of a class. So there is a thing called type classes in Haskell, which we are not going to talk all that much about during these 2 days. But type classes are essentially common interfaces that many types support, so that you can use the same function names for similar functionality on different types. And it's not, like Haskell is not an object-oriented language. You don't that often declare your own classes or something like that. Most of the time, type classes are used for interfaces which are really ubiquitous, like types that can be serialized into strings, which is almost everything. Types that can be compared for equality, which is almost everything. Types that allow some kind of ordering, which is almost everything, right? They're really, and so most of the interesting type classes are already defined. Even though you can define your own new type classes, it's a far less common thing to do than defining your new data types or defining functions, right? The most interaction you get with type classes is that you are actually instantiating existing types or types that you're defining yourself to already existing type classes. So how do you do that in this case? You write instance show card color, and then you have to know what are the class methods of the show class. In this case, it's one, which is relevant, which is the show method. And you say show equals show color, which we already have. And now you've made card color an instance of the show class. And now, because the show class is an interface that is used by other stuff within GHC, now if you're actually typing yellow and just evaluate that, then GHC will use the string that you used here in order to print back the value to you. So if we had defined this here to be something different, something like green with a lowercase g, right? And not recommended, but it would actually show up there, right? Okay, so let's go back. Okay, so now this function is boring, right? Because you could ask yourself, why cannot the compiler do this itself? I mean, we have the names of the data constructors, and we're using exactly those names as the strings. And the good news is the compiler can do this itself. So you would typically not do this like that. You would instead just write in the data definition, you're deriving show. And now I'm getting an error message because this deriving show will also create a function that shows card colors and make an instance declaration that uses that function. And now we have 2 instances for card color show. One is the derived one, and one is the one that we defined ourselves. So if we want the derived one, we should get rid of this one. Okay. And now this function here is loose, right? I mean, this still exists, but now if I write green here, this is not the one that I'm actually using if I'm printing back values. Like if I evaluate yellow, it will still print back yellow because the derived show instance does the obvious thing, right? It uses exactly the names of the constructors in the function definition. Okay? So that's a thing that you'll do typically, right? I mean, if you define a new data type, in most cases you will want to derive show for it. And as we shall see, often quite a number of other type classes as well, such as equality, for instance. We'll get to that, right? Because very often you want to check whether two colors are equal, right? So there are a number of type classes that you can do this deriving for, but that's the compiler magic, so to speak. This is not a completely extensible concept. There are a number of select type classes where there is an obvious definition that more or less follows immediately just from the data type declaration. And in those cases, you can derive the instances. You could perhaps also ask, why doesn't the compiler do this automatically for every type? But this is a safety aspect. Sometimes you want to restrict functionality. Sometimes, even though you could compare two values for equality, you might want to say, this is not something you should do with things of this type. Or sometimes you might say, I don't want to show, be able to serialize values, because you want to keep the interface small and simple and say there's only a very limited amount of things. So it's just a way of giving you more control. Okay, so this is all hopefully very basic, but nevertheless, any questions up to this point? Yes.
Yeah. So if you do the deriving show,
yeah,
you want to override just one value.
Mm-hmm.
How would you do about that?
So the question is, if you want to do the deriving show, but you want to override one value. This is actually a very good question, and one I still find this painful from time to time. You currently don't have a really compelling good way to do that. I mean, so you can either use the derived show functionality, or you can define your own. But you cannot easily get the derived show functionality and then still somehow modify it. I mean, there are some tricks in order to achieve something like that, but they are already rather fancy, advanced, evil stuff in some sense. So I don't think there is a very good answer to that. But I mean, I feel the pain. I mean, it's something that I also often want. It's not that easy to achieve, unfortunately. But in many cases, it's not necessary, because there is the intuition of show is to actually, and that's also why you typically use the derived show instances, is a little bit development oriented, is to produce a textual representation which is itself a legitimate Haskell expression again. So that in principle, you could just use it in your Haskell program. It is not really intended to produce sort of a human readable or user-facing textual representation of something. For that, you would typically use different functions in the first place, right? Any other questions? Yes?
Not a question, but something I noticed. To run this Cabal REPL, you have to be in the day one.
Oh, yeah. Yeah, so the remark is that in order to actually use Cabal REPL, or also if you want to open the file in the editor, you typically should be in the directory that has the Cabal file in it, and that in this case is the subdirectory day one of the Git repo. Yeah, that is correct. Thank you. While we're at it, anything else? Okay. All right. So. Yeah, so I already did step 4, essentially. But one other thing that you can do is you can ask the eval plugin, or also GHCi, for inferred types of expressions. So you can put something there which starts with this special :t command, and then it says, the meaning changes. It doesn't say evaluate this expression and give me the value back, but it says, give me the inferred type for this expression. And it always repeats the expression that you typed there. That's normal. And then it writes the double colon, and then here you get the inferred type, right? So everything in Haskell is statically typed, but you typically have type inference. That means the compiler tries to figure it out itself, right? And in many, many cases, the type inference is actually quite impressive. In this particular case, I think we would all have expected it to be able to come up with it, but we'll see more of that. Okay, so step 5 we've also already done, like I've demonstrated the deriving show. So next one is that we want in our card game, we want to associate scores with different cards. So, and as a starting point, colors and ranks are associated with a point score. Or should I have defined ranks already? Did I skip that?
Step 5.
That's step 5. Ah, I see. Is it? I don't know. I'll just define it. I mean, let's define ranks as well. Rank is another type. So rank, we said we have 3 different values. We have 1, 2, and 3. And you could be motivated to, here we say, you could be motivated to use integers, right? And it would work, but it's not very precise. And there is a little bit of trade-off here. But typically, if you have very few different choices, and you're not even yet sure whether you want to do a lot of computation with these ranks or whether you're just using them to tell things apart, then you would rather be precise. So here we can just define another enumeration type, which has 3 different shapes, and I'll call them rank 1 to rank 3, and I'll also derive show for this. So this is just more of the same, right? So now we want to associate these scores with colors and ranks. So now we say yellow is 10 points, red is 20 points, purple is 30 points, and black is 100 points. So this is just another function, right? So this is hopefully nothing new. So we do something like color score. We choose a name for the function. We define a type signature. By the way, these type signatures, they're optional. I mean, I can demonstrate that in just a moment. But it's strongly encouraged or recommended that you do this, because I also always think it's a design concept, right? If like solving a problem is hard, but solving a partial problem is often easier. And actually thinking what type should the function have that you want to define is a significant part towards defining the function, right? Like making sure, like, do I have an idea what the inputs are, what the outputs are, what is the kind of stuff that even like plays a role? And once you have the type signature, that leads you to writing code. So if we write color score, we want to go from a card color to an integer. And this is another pre-existing type, which you have. And now that I have the type signature, right, now again, I'm almost like guided, if I have a little bit of experience, towards doing this pattern matching, because I know I have a card color as an input. And so the natural thing to do is to do pattern matching and to say for all the different shapes, what is it that I want, right? What is the score for yellow? What is the score for red? What is the score for purple? And what is the score for black? And now in this case, it tells me that I need an int. And so, and this is one of the reasons why the type signature is actually helpful, because if I wouldn't give the type signature, then at this point, right, it's an okay definition in principle. I get a warning here. The warning tells me exactly, this is the yellow squiggly line. It would tell me exactly that I haven't given a type signature, right? But in particular, if I look at the error messages for the holds, I'll just get some variable, some type variable, right? Because currently, there's no further information about what we actually want to do. If we have set that up front, then we get more helpful information. And that's typically the case, right? If you write a type signature and then make a mistake, you get a better error message than if you don't write a type signature and make a mistake. Plus, it serves as automatically checked documentation and so on. Makes everything easier, right? So a score for yellow is 10, score for red is 20, score for purple is 30, score for black is 100. Done. Okay? So similarly for ranks, this one should hopefully not come as a surprise. Rank to int, more of the same. rank 1 is 1, rank 2 is 2, rank 3 is 3. Okay? I mean, any questions? Still with me? Okay. Okay, step 8. Actual cards have a color and a rank, right? So far we have defined the data type for colors and the data type for ranks, but if we actually want to talk about cards, then we should have a data type that captures this. So we define a data type for card, and this is another common case, right, of the general data type. So I said data types in Haskell always have several possible shapes, and each of these shapes has a name. And we have seen one common subcase of data types is their so-called enumeration types, where you have a number of different shapes, and there are no further arguments involved to any of these, right? It's simply basically a choice of several different values. Another common subclass are so-called product types, or you can also call them record types, although this isn't strictly speaking a record yet, which have just a single shape. And I'm going to call the shape make card at the moment, or MK card, as a common convention, but it's your choice what you want to call this. But now you have arguments to this single shape, and the arguments are the types of the things that you want to group there. And this is a card color, and card, actually, perhaps I should also have called it card rank, but I called it rank. Let's keep it at rank rather than change it. Okay. Okay. So this is another piece of, I think, mostly confusing syntax, actually, right? Because, again, like we have uppercase identifiers. By the way, okay, I should have said function identifiers always have to start with a lowercase letter, right? So that this is for the first character, you have rather strict rules. For the rest, you don't. But function names should always start with a lowercase letter. But here you have things that look the same, all next to each other. Make card, card color, rank. They all start with an uppercase letter. But the syntax highlighting gives a clue, right? The first one is different from the two others. The first one is the name of the data constructor, the name of the thing. And the other two are the types of the arguments of that data constructor. Yeah. You can even, and this used to be extremely popular in Haskell, you can give the same name to the data constructor as you can give to the type. They're still two different things. They also have two different colors. But they typically occur in different worlds, right? Types occur in type signatures and in inferred types and whatnot. Data constructors occur in the actual expressions that you're writing down. So it's kind of okay that they have the same name because it doesn't really clash. But it leads to confusion, and plus Haskell is gaining more and more features that actually blur the distinction between types and terms to some extent. So therefore, it's becoming less popular over time. And I'll usually not do this. I'll always try to choose different names for data constructors than types to keep them more clearly apart. So now we come to an interesting question. I mean, so perhaps, let's first do something simple. I'm going to derive show for this. And then I'm going to do a make card, and I'm just going to test this out. I'll apply this to red and to rank 3 and see that this is printed back to me, right? All the components have show instances, and this is a valid expression. And if I would, for example, I don't know, put a different thing here, if I would put another color here, let's say purple, I would get a type error instead, right? It would tell me that there is an expected type rank at this point, but I've actually given a card color, right? So this is good. Let's go back to this. And if I ask for the type of this, make card red rank 2, then perhaps also unsurprisingly, I get card. So interesting question perhaps, what is the type of make card? What do you think? If I don't apply make card to anything, what's the type of that? Yes?
It's a wild guess, but I would say it's kind of like a function that will take two things and that will return it out.
Yeah, so the suggestion is it's a function that will take two things, and yeah, and in particular a card color and a rank, and it will return a card. And that's in principle exactly right. It's just that in practice, the way this looks like may be surprising to you. So, but what you said is still correct, right? So it's this is the way that functions with multiple arguments look like in Haskell. And there is a reason for that, right? So you basically write the first argument, then an arrow, then the second argument, then an arrow, then the final argument. The reason for this is a concept which is widely known as currying. And the idea is that conceptually you can get away with pretending that functions always have one argument. They never have more than one argument. But functions can return functions. So if you just say, you pretend that you have a function that expects a card color, right? That's the first argument, that's the type of the first argument. But then it returns a function that goes from rank to card. Well, then you can directly, after you've applied it to the first argument, apply it to the second argument, and then you have a card. And this is cute, perhaps, but it's also actually useful because quite often, we'll see examples of this later on, quite often you'll have situations where you want to apply functions to some arguments, but not all of them. And you can do that simply by writing a partial application. The syntax with the spaces is actually very useful for this, because if we write make card space and then we apply a color, right? There's only spaces, so this is an application of make card to one argument, and that's a perfectly legitimate expression. That's a function from type rank to card, right? We have supplied one argument but not the other, so we have the remaining function left, and if we supply the second argument, then we have seen that up there already, right? Then we have supplied all the argument, and we have a card left, and that extends to arbitrarily many arguments. If you have a function with 8 arguments, you have like 8 different types, all function arrows in between. You supply the first, you have like a function which still expects 7 arguments left, and so on and so forth, right? That's the overall idea. It's unusual, but it's also quite nice, because it really means that you don't have to directly track the arity of functions. The function arrow is taking a single type to the left, a single type to the right, and it just extends naturally. If you're worried about performance, the compiler is still doing arity analysis and checking how many arguments does the thing actually need. It's not actually going to supply arguments one by one internally, but that's for the compiler to worry about, not for you. Okay. So now, score of a card. Score of a card is the sum of the score of its color and the score of its rank. All right? So we start with a type signature. We want to start with a card. We want to compute a score, which is an integer again. Now what? It's still the same principle, right? And this is really the biggest thing that I actually hope you take away from this first day, is that pattern matching follows the same idea regardless of data type all the time, right? So previously we had a data type like color, which has 4 different data constructors. So we have 4 different cases. Now we have a data type that has 1 constructor, so we have just 1 case, but the pattern for this make card constructor can now take patterns for the arguments. And you could actually go on and now make a distinction here again on different colors and different different ranks if you wanted to. You could put all the different, like enumerate all the different cases. But that's not actually necessary. And if you want to like write a pattern that matches anything, you can simply put a variable there, right? So I can introduce a variable for the color, and I can introduce a variable for the rank, and then put a type, a hole here on the right-hand side. And now these are in yellow underlined because GHC produces warnings for things that I've introduced but not used. So currently I've introduced color and rank, but I've not actually used them. That generates warnings. But I'm also getting, well, I mean, perhaps not very readable, but I'm getting a relatively informative error message, right? Because, again, this is gradually becoming more informative and more helpful the more complicated the programs we write are. But now we do not just get a message that says we have a hole which is of type int, but we also get the types of all the locally in scope things that we have available in order to construct that int, right? So it tells me that, oh, you've just introduced a variable color which is of type card color. You might be able to use that. And you've just introduced a variable called rank, which is of type rank, right? So it becomes a little bit like a puzzle game, right? You have a number of things of certain types available. You can use that to construct the result that you're interested in. So in this particular case, we want to create the sum of two things. I can actually even write it like this and have two holes here. Then in both places, I need an int. And on the left, I want to have the score of its color. That is color score of color. And on the right, I want to have the rank score of the rank. Does that make sense? Do you have questions? Okay. So sometimes we also want to just access either the color or the rank of a given card, right? So I get a card and I want to determine its color again, or I get a card and I want to determine its rank. And we can always use pattern matching in that situation, but we can also, and sometimes that's in certain situations more convenient, define dedicated selector functions, right? These are very trivial to define. We can define card color, which is going from card to card color. And again, we have a pattern match, color, rank, and we simply return the color. Now we are not using the rank, and that's intended, and we are getting this warning that we've introduced rank and we're not using it. There are two options to get rid of this warning. One, or they're related options. One is to just use a so-called wildcard pattern. A wildcard pattern is an underscore. It matches anything like a variable, but you cannot use it afterwards, right? That's, you're saying, I want to discard this. There is also the option of using a name that starts with an underscore. Then you'll also not get a warning. But this is, I mean, this is actually advantageous because you can say, I don't want to use this, but a useful name for it would be rank, so it's slightly more informative, right? Like in particular, if you suddenly have, I don't know, 5 wildcard patterns right next to each other, it might be helpful to the reader later if you somehow say, oh yeah, but this is actually this thing and this is actually that thing. Perhaps unfortunately you can actually, this still introduces a name. Like the wildcard pattern really doesn't introduce a name. This is actually underscore rank you could still use on the right-hand side. It wouldn't actually be forbidden. You just don't get a warning about it. It's a convention, so to speak, right? The wildcard patterns are special, they're built into the language, whereas the fact that you don't get a warning for an introduced variable that starts with an underscore is just a compiler convention. That, but nevertheless, I mean, one of the two you should be doing, and this is to signal intent, right? That you acknowledge that you really don't want to use this, right? And similarly for card rank, you get from card to rank. Make card color rank is rank. Okay. Typically, you'll not see people write these selector functions out by hand. The more common way to do this is by introducing the data type with field names in the first place, and that means turning it into an actual record. So what you can also do is you can write card color here and card rank here. And you have to put these curly braces and the comma in between. And the important thing is that a record in Haskell is still just a single constructor data type which has two positional fields. So you can use it exactly in the same way as before, just the derived show instance will actually be different. So if I do refresh here, oops, what is it doing? Wow. Okay, interesting. Oh, I have errors. Okay, yeah. Okay, so I have errors and I try to invoke the eval plugin. So that sometimes yields strange error messages. So, I mean, of course, because the record declaration introduces these selector functions automatically with exactly the definitions that we had here. I'm going to comment them out now. That's the big advantage we're getting from defining the record, that we have actually card color and card rank in exactly the form that we had before as selector functions available, and we don't have to define them ourselves. But I can still construct make card red rank 2 like this. It's only that the show instance will now print it back with the record labels in there. And this is actually another valid construction syntax that you could also be using, right? So these are interchangeable. You can either apply the arguments to a record type positionally or via the special record syntax. That's your free choice, right? But the show instance is more verbose. And going back to the question about modifying show instances, this is one of the reasons why I occasionally actually define certain selector functions by hand, because sometimes I find this show instance too noisy and I'd rather have the one without the explicit record labels, and then I still define selector functions by hand instead. Yeah, so that happens. There's a lot more to say about records. Also, records have been, there are some extensions to the Haskell language in recent years that make working with records much more convenient, but it's not really relevant for this introductory course. So let's leave it at that, unless there are questions, of course. Okay. I'm slightly worried that I've already lost you all because I'm getting no questions anymore. Okay, good. Step 11. So let's do another function on cards. We want to have a different, I said like sometimes you want a user-facing way of representing cards rather than a program-oriented way of printing cards, right? Because now if I evaluate an actual card, as I showed here, I get a rather lengthy string back. So this is probably not the way that I would actually want to show a card on screen, even if I'm just interested in a textual and not a graphical representation. I probably want something more compact. So like just as a simple exercise, let's define a more compact representation where the idea is a color is just represented by its starting letter, and then the rank is just specified by the actual number of the rank, right, without the word rank. And then we want to combine these two things using a dash, right? So this is a few more functions we can practice with, right? I mean, so compact color is going from color, or from card color to string. Pattern matching, 4 choices, yeah, yellow. I'll fill them in immediately without holes in this case because it's so simple. Compact color of red is red. compact color of purple is P, compact color of black is B, right? And then we do, we could do compact rank as well, would only be 3 cases like this. But we can also just use the show instance for the value, right? Because the rank matches, I mean, this is actually a trade-off, right? I mean, sometimes you can reuse nice stuff, so you could argue, oh, we've already defined the value of a rank, and the value of a rank is really the obvious thing, so we can just use the show instance to turn a number into a string and use that. But you could also say, oh, but perhaps somebody later says that the score of a rank is not exactly the rank, and then that definition would become incorrect, right? But that now we're going more from sort of learning Haskell into software engineering aspects. And in this particular case, I mean, I can guarantee that for the rest of this course, this definition will not change. So just to show different styles, I'm going to use the show instance, and the compact card definition could be defined like this. And compact card is make card color rank. And now I'm going to use compact color of the color. And now I want to append strings, right? I need something to append strings. So there's an operator for this, which is called plus plus. And then I can put a string, which is a dash, and then I have another operator, plus plus. And I can use the show of the what did I say, of the rank value of the rank. Oh, what was it? Rank score. Now here, this is a typical case, or actually also the pattern matching as well, right? This is a typical case where you do use parentheses, right? I just want to point that out. Why am I putting parentheses here and not anywhere else? It's because if I would not put the parentheses here, then it would be an application of show to 2 arguments, right? So show would be applied to rank score and rank as the second argument. And you can say, well, wait, but rank score is a function. But that's the point. Haskell is a functional programming language. Functions as arguments to other functions are perfectly fine, and it will happen, right? There are situations where you want exactly that, to pass rank score as the argument to another function without applying it. We'll see that. But here, yeah, so show has 1 argument, and it's a compound thing. And if the argument is compound, then you do put it in parentheses to group it together. But you still use a space. I mean, again, this is not strictly needed, but everybody will be able to identify you as somebody who's new to Haskell if you don't put a space, right? Okay. So we've seen quite a number of operators already, right? Plus plus is an example. We've used plus, we've used times, or did we use times? Perhaps not, but we used plus. So it's a question like, what are these, right? Are they also functions? And if so, are they special functions? So it's a useful thing to know. So we can look at a couple of, let's actually start one step before, and let's start with this function show that we've already been using, but I've never actually shown the type of show. So the type of show, let's first just pretend that this stuff, this beginning part here is not there. The type of show is, as an approximation, is a to string. So it's a function that returns a string, but it takes a type variable as the input type. And type variables can be recognized. Again, uppercase, lowercase letters are terribly important in Haskell. Type variables always start with lowercase letters. Types start with uppercase letters. So this is something that you can choose. Whenever you call the function show, you as the caller can choose an arbitrary type to call it on, except that it is not completely arbitrary. There is an additional constraint, and that's this part. It says that A actually has to be an instance of the show class. That's a condition. So that constrains the choice that you can make for A, right? And so that's how you read a type signature such as this. Similarly, we can look at the type of plus addition. Now, a syntactic thing about Haskell, which is, you can say it's elegant or confusing. I personally think it's rather elegant, is Haskell does not have a built-in set of operators at all. You can define as many operators as you like. And operators are just functions, but they follow a slightly different syntactic convention. So identifier names fall into one of two classes. They're either alphanumeric, which is basically nearly everything we have seen so far, or they are symbolic, which means they consist solely of a predefined admissible set of symbolic characters, an arbitrary sequence of such characters. And plus is in this set of symbolic characters. And if an identifier is symbolic, then by default it is used in an infixed position between its two arguments. If an identifier is alphanumeric, by default is being used in a prefix position, like the function applications we are typically seeing. But you can flip that default around in both ways. So the way to turn an infix operator into a prefix function is to directly enclose it in parentheses. So you can write parentheses open plus parentheses closed, and then you can just apply it to its arguments. I can even show that before I show the type, as if it is a normal function. You can say like, okay, 2 is the first argument of plus and 5 is the second argument of plus, so it is 7, right? So you can do that with any operator, right? Similarly with plus plus, if I say plus plus of foo and bar, then it is the concatenation of foo and bar, okay? So, and also if you want to ask for the type of just the operator without applying it to any argument, you have to put these parentheses there. Otherwise, it won't work. And now we get this, and it's perhaps actually already readable with all the information we have so far. So basically, again, let's first look at it without the double arrow, right? It's a function, curried function with 2 arguments. Operators typically have 2 arguments, although in theory they could have more, right? Because you could like write 2 things and put an operator in between, and the resulting thing is still a function. It's perfectly fine, right? But typically they have 2 arguments, and so they both have to have the same type. That's the type variables still convey a notion of sameness, right? So you can choose a type to use plus on, but both arguments to plus must have the same type, and the result will then also have the same type. And there is a constraint on that choice, namely that it must be a numeric type, right? That is what the num class symbolizes. And the num class has instances such as int, we've already seen int, double, integer, which is a version of int, which is unmemory bounded. Leonard has shown integers in his talk briefly, like he mentioned that who needs very large integers, right? but they're available, and yeah, so and complex numbers are also an instance of num, and I think they are also an instance of num in Haskell, and so on. So you can have a number of instances there, right? You can also look at the type of plus plus. This is mentioning a type that we haven't seen yet, but we'll see later. Which has a little bit of special syntax, but this is essentially, it takes 2 lists of an arbitrary element type and produces another list. And strings are actually just lists of characters. There are different string types in Haskell, but the ones that you have available, if you don't import anything and don't use any libraries, are just lists of characters. But we'll get back to that. But here you see an example of a function which is fully polymorphic, or sometimes in fancy wording, this is called parametrically polymorphic. You have a type variable which is really free to instantiate to whatever you like, because there's no other constraints. So this works on lists of whatever element type you can think of. The element type doesn't matter, right? You can, as long as you have two lists that have the same element type, you can append them, and you'll get a list of the same element type back. But it could be a list of functions, it could be a list of strings, it could be a list of booleans, a list of whatnot, right? I mean, you have arbitrary choice there. But, okay. So, how are we doing with time? Officially, it's until 3:30, right? 15:30. Yeah. Okay. Yeah. Okay. That's good. It's not. Yeah. It's not too bad. Any questions? Yeah.
Is it possible to define a plus on some type which is not a number?
The question is it possible to define a plus on some type which is not a number? I mean, yes. I mean, first of all, you can always reuse names that already exist. You're not, I mean, you can hide the predefined definition of plus completely and define your own completely separate version of plus, which still looks like a plus and has a completely different type, right? Doesn't even have to take two things of the same type, can like be a plus between one thing and another thing, right? That's one option. The other option is also that in principle, nobody prevents you from defining weird types to be instances of the num class. that might be confusing, right? But there's nothing in the language that intrinsically prevents you from that. Num is a bit of a weird class anyway. Many people don't like it. It's not sort of like very mathematically designed. It has it is a quite large interface, and it's not very convenient to do it for things which are very far away from numbers, because it, for example, requires you at the same time to define plus and times and a mapping from integers into whatever type you have, and so on. So a couple of things which might very easily get very tricky to define if you're defining it for something exotic, even though you might want to say strings, you want to use addition, right, rather than the double plus for append or something like that. But that would not be nicely fitting within the num class. But yeah, I mean, you can always get rid of the predefined stuff and define the same identifiers to mean something completely different. That's perfectly fine. Other questions? Okay. All right, so let's do more practice. Let's say a combination. This is just a term which we are going to fill with meaning. A combination of cards is either a pair or a triple of cards. And we want to define a data type for this. So I'll define a data type combination. And, I mean, I've suggestively explained this. It has two different shapes. I mean, there are different ways to define this, right? But I mean, I'm going to be very direct. It has two different shapes. One which I'm going to call pair, and one which I'm going to call triple. And both these shapes have arguments. A pair has a card and another card, and a triple has a card and another card and a third card. Okay? And then I'm going to derive show. Does that make sense? Right? So this is just, I mean, this is not falling into the special classes of data types, but it's actually demonstrating sort of the general structure of data types, right? Very often data types fall into one of these special classes where there are either enumeration types, where you have a number of different shapes or constructors, and none of them have any arguments. Or they are record or product types where you have a single constructor which then has arguments. But you can have any combination of this. You can have multiple shapes, and some of them can have arguments, some of them can have more arguments, some of them can have no arguments. This is all fine, right? So now you have two different shapes, and one has two arguments and one has three. And we can ask what is the type of pair. And hopefully that is not surprising now. pair takes a card and another card and then gives you a combination, right? And then triple takes 3 cards, hopefully. Oops. And then gives you a combination. And here you see currying really extends to more and more arguments, right? You just always put the function arrow in between. But again, this stuff still works, right? If I define, and let me define an actual card here. Let me define something like example card of type card. Example card is, let's say, red and rank 2. And now I have that example card, and I can ask what is the type of triple applied to example card twice, right? Then it's a function. Here I had like one card which I've supplied and a second card which I've supplied, and what's left is a function that wants one more card, and then I have a combination. Yes?
So I noticed that you have to set the deriving for combination, but that is already set for cards. So is there a notion of that happening automatically, or would that contradict?
So the question is, I've said that I want derive show for combination, but I've already said it for cards, and whether that could be automatic. So I think I briefly mentioned that you always want control over what functions you really have available over a data type. It's just better if you are in full control, if you potentially can define a data type that has nearly no operations whatsoever. So you always have to be explicit. But of course, it is a prerequisite for this deriving show that the cards are deriving show. If I had no show instance for cards, then this one would fail, right? I can demonstrate that briefly by just defining yet another data type. Let me just say data other equals make other, and I'm not deriving show for this, and I just put an other as a third argument here, then I'm getting an error message now for deriving show that actually complains that it cannot derive that instance because there is no show instance for other. Okay? Yeah. Yes? Okay, the question is whether the names of the constructors have to be globally unique. Just like with plus, they don't have to be, right? So you have namespace management on a module level. So basically, there is a number of things which you don't see are actually imported into every module by default. There is one specific library in Haskell, which is called the Prelude, and that's a special library, which is imported by default. You don't actually have to say that you import it. And that is why we have things such as show or plus or double plus or all these things already available. But you don't have to do that. You can still be explicit. You can import more things here by specific import declarations. And you can also do a specific import declarations for Prelude that says, this is a special case, as I said, because Prelude has a default, which says I want to import nothing from the Prelude. That's the syntax for that. And if I do that, then suddenly everything becomes wrong now, because it says, oh, I don't know what show is, right? But in that sense, you can also hide existing constructors again. You should not ever define two data types that have the same constructor names within a single module. Then you're really in trouble, right? But, yeah. Any other questions? Okay. Where are we? Okay, so we have our combinations. So let's define scores for combinations. The score of a combination. So the idea here is, right, trying to make it slightly trickier. In principle, the score of a combination should be the sum of all the scores of the cards involved, except if all the cards in a combination have the same color, then this original score, which is the sum, should be doubled, right? A combination which has like all cards of the same color should be has a higher score, like has double the score. So we do this in steps, in sub-steps. So what we actually do first is we define this original score. I call this plain score, which is like the default score that a combination has. Let's define this first. Plain score is going from a combination to a score. And how many cases do I have to write? Two, yeah. I mean, number of constructors, right? Pattern matching, 1 case per constructor. That's the default thing. I mean, of course, it doesn't always apply, but it should always be the default, right? If you're having an input, you have a data type which has 2 different shapes. Then here, pair, card 1, card 2, plain score, triple, card 1, card 2, card 3. Okay. Oh, score is int. Yeah. I mean, there's an argument to be made. I did not want to overcomplicate this. That we should actually have introduced a separate type for scores as well. Like it's a good habit in Haskell in general to define new types for almost everything. And there are many different things that you could be using integers for. And scores might have particular properties that even though you don't explicitly represent them in the type, you still want to establish effectively as invariants. For example, you could have an invariant that you say scores should never be negative, I mean, or something like that, or something around those notions. And it might just make sense to actually define a new data type, but let's not go overboard. But in general, that's a good idea in Haskell. New data types are cheap, right? So so here we have to say what is we just wanted to have the sum of the scores. That was the plain score. So we basically just use the card score of card 1 plus the card score of card 2. Why not? Or did we not define the card score, or did I call it different? Ah, right. Thank you. And then let me do it like this. Oh, I should also say something about layout. So this is something which is easy to forget because I won't make any mistakes, but if you're writing Haskell programs for the first time, you're almost certainly going to make mistakes. So Haskell uses layout in order to delimit expressions, and the exact rules of layout are relatively tricky, but by definition or by like sort of intuitively, the things that are most important to us so far is that all the different clauses of one thing that like belongs together, like plain score's type signature and the entire definition of plain score, they should all start at the same column. In fact, actually, all the top-level declarations of the same module should all start at the same column, which in this case is the very first column. And then all continuation lines of each clause should actually be indented more than the lines that they like continue, right? So I should not be putting this at the very front of the line, then I would get a parser error, which is parser errors in Haskell are typically rather bad or relatively cryptic. I mean, people might justifiably say that type errors are very cryptic as well, but actually they become less so. If you understand a little bit about the type system, type errors become rather understandable, but parser errors are often really bad. You just have to stare at the code and see what's wrong. Yeah, so that's that.
Does it have to be 2 spaces, or it's custom as long as it's consistent?
The question is it custom to use space? Yeah, so it is very strongly discouraged to use tab characters in Haskell source code. It is possible still, I think. I think there is actually a warning. Probably there is a warning, but it's not an error. And in theory, you could be entirely consistent, but it's it's weird, and typically then you often get into a situation where you have a mix of tabs and spaces, and the Haskell compiler, I think the standard for some weird reason says that every tab is then seen as 8 spaces, which is not at all a common tab length in editors these days, and it just leads to lots of confusion. So just don't use tabs in Haskell code. Yeah. Oh, there are no linters to try to mitigate. No, in fact, I mean, it's just Haskell, Haskell is an old language compared to many other more modern languages. Haskell is actually around for quite a while, even though it is sort of in spirit still a very modern language. And in some other aspects, it's not. And sort of like the old days of Haskell far predate sort of the times when basically a language definition comes with a default formatting discipline and ships with its own default formatter. So what you see is that there are a number of formatting tools available, but people don't necessarily agree on which one is the one they want to use. So in practice, I think most companies are agreeing on a standard formatter, but different companies or different projects might agree on different ones. And there's not one completely globally consistent style. Obviously, the formatting engines and the linters, they might still pick up on layout errors or reformat stuff in such a way that the layout becomes very visible. But yeah, I mean, the situation is a little bit different than if you just have basically one default way of layouting. And I'm also old, so I've never started believing in auto-formatting myself, so I don't use them if I can avoid it. I mean, if I work for a client that forces me to, I will, but in my own code, I never do. And one of the reasons I don't like it is that sometimes I like to highlight symmetry within the line, like to do so, like which is also, I know many people dislike this, but to do sort of horizontal alignment of things that correspond to each other, and auto-formatters typically destroy that sort of stuff. And anyway, right?
So you have like a limit of indentation, like what if you want to indent stuff in multiple levels?
What if I want to indent stuff in multiple levels? I mean, you can just do that. I mean, I can in principle, I mean, there are certain things which are layout sensitive, but others are not, right? I mean, actually, for example, for these, the relative indentation of all these things is completely unimportant, right? The only thing that matters is that all these continuation lines are indented more than this original line. But there are other constructs which are sensitive to layout. We'll see more of them, like let and case or something like that. We will see them, but many things are also not, right? You have to learn this over time or read the actual specification of the layout rule. But I think it's not worth looking at the exact definition in here in this intro lecture. Yeah.
Could you leverage the definition that you already said for the plain score of a pair when defining triple?
Could you leverage the definition I've had for a plain score of a pair in the score of a triple? Yes, but I don't think it would win me very much here. But I mean, I could, if I wanted to do something like call plain score again on pair card 1, card 2, and then add the score card of card 3 to it, right? That I mean, that is technically possible, but in this case, I don't think it actually makes things easier to read, right? So I would not do it. Was there a follow-up question somewhere else, or was it just no? Yeah.
Are there other ways to make these definitions less repetitive?
Are there ways to make this definition less repetitive? Yeah. Although I think I'm basically making a choice with the data type declaration, right? I think the real question is here. right? If I knew for certain that this is what I always want, and also like slightly depending on what I actually want to do with these combinations, if I in the end want to treat them always similarly, or whether I want to treat triples completely differently from pairs, it may make sense to do a different definition of combination where I say something like make combination, which is only one thing. By the way, prime, like this character, is just an admissible identifier name. It doesn't have a special meaning. I'm just defining a variant of the original thing, right? And I could say something like, okay, a combination is 2 cards and then another optional card, right? And there is actually a type in Haskell which we'll also see for this, which is called maybe. And this would be a different definition, which is also good for combinations if I really just want these 2 cases. And it may lead to better code, it may lead to less code, right? I think this is basically my main message here is always that you should be encouraged to define data types, and functions want to follow the structure of the data types. That's the natural thing that you want to do. And if you're ending up with functions that are ugly, then very often you should question yourself whether you have defined the wrong data types. Right? So very often the way of least resistance then is to define a different data type, perhaps even temporarily a different data type. Sometimes you want to have 2 different views on the same thing, right? Certain stuff is easily expressible on one data type and other stuff may be more easily expressible in another. Well, yeah, you can define these 2 data types. You can define conversion functions between the 2. You can use the one which is more convenient for whatever you want. Yes?
So we might want like a to-list function on combinations.
You might want something like a to-list function on combinations. Yeah, that is also an option. So you can say that if in the end it's not actually very often very important that you have only 2 or only 3 things and you just want to treat them as sort of a combination of things, then you might want to write a to-list function on cards. I'll not write it right now, even though I like the suggestion, but because I still haven't actually properly introduced lists. That's my main reason. And I don't want to inject all that yet, right? But it's a good suggestion, yeah, absolutely. Okay, so okay, yeah. So my interlude statement here can go because we have introduced currying a long time ago. But now we need, because we said like, okay, the score should actually be doubled if all the cards have the same color. We need a way to check whether 2 cards are of the same color. And I've already said that there is a type class for this and that this type class is derivable. But just like for show, let's once define an equality function ourselves so that we understand how we could do it if we ever wanted to, right? So how do we check whether 2 cards are of the same? This is a function which has 2 arguments. This is probably the first curried function that we're really defining ourselves, right? So it's the first function with multiple arguments that we're defining ourselves. So it takes 2 cards and it produces a bool, which is another existing type, as an output. Unlike the existing types that we have seen so far, like strings and integers, which are really a little bit special because they are kind of relatively primitive and built in, bool is a data type that is completely normal, like any of the data types that we've defined so far, and you could easily have defined it yourself, right? The definition of bool is simply data bool is false or true, right? And that's it, yes?
If this is just about the color, should it be called equal cards?
Oh, that's just my mistake. Thank you very much. I mean, the remark was that I said in the comment, I want to check whether two cards have the same color, but then I use cards. All right, so let's be slightly more systematic. I know this costs time, but I think it is also one thing that I see always again with beginners is that they struggle because they don't do things systematically, right? So try to be systematic. So actually, I've been even glossing a little bit about this. So you can really just start with defining the function to be a whole. Then the whole actually says, oh, you have to put the function here, right? I mean, equal, okay, fair enough. So you introduce arguments, color one, let's keep it short, C1, C2. Now you have two arguments on the left-hand side. They're both variable patterns, they match anything. So you still have one thing, which is a bool. So sometimes you are in situations, in particular when you progress and you know more functions that you can reuse, where you can, like, in one sweep, define an entire function in just one line, because you can just invoke other functions and somehow plug the result together. But the common thing is that we need to do pattern matching. And in particular, if you have multiple arguments, you should typically do this systematically. Now, here equality is still simple, so we can kind of see where we want to end up at. But you probably want to pick an argument, and very often the first, and just do an exhaustive pattern match on that one, right? And so we can write these four cases, like yellow, equal color, red, equal color, purple, equal color, black. And now, in principle, if you wanted to be really systematic, you could now go on and say, well, in order to distinguish or to see whether these colors are equal, I also need to analyze C2. So I need to make another four cases here, right? So where this one is yellow and this one is red. Don't worry, I'm not going to write all the 16 cases, but I'll demonstrate it up to this point. Color yellow, purple, and equal color. And you could, right? And it's good to know that you can, because sometimes you can be clever and save code and so on, but the simple thing would have still saved you time because you wouldn't have made any mistakes, perhaps, right? It is always a trade-off. So just be aware that you can. And then you could start filling these, right? This one is true, and this one is false, and this one is false, and this one is false. And now in this case, you see that there will be very few cases which are true, and very many cases which will be false. In fact, there will be exactly 4 cases which are true, and all the others will be false. And this means that it is actually more useful to just consider the cases that are true and then have a catch-all case in the end, which maps everything else to false, right? But this is a simple example, and I would really caution about sort of the premature introduction of catch-all cases, because, right, they are harder to reason about. Suddenly you have things that are where the order matters, right? If you match exhaustively into different cases, the good thing is every line is understandable in complete isolation. If you have overlapping cases, if you sort of match on one thing and then in the next you just put a variable, or like in the worst case a wildcard, then the exact meaning of when the second case applies depends on what comes before, right? And that's more conceptual overhead. And for more complicated things, that's harder to reason about. So it can be useful, such as here. It definitely is here. But it's not sort of something that should be done entirely without caution, right? So here, the best way to define this is to list the 4 cases which are true explicitly. Black is true. And then have one catch-all case, which says in all the other cases, it's false. Okay? And that's the definition that will also be derived, right? And then the instance declaration, you can again make an instance declaration for card color for equal, where you say the equals operator is just defined to be equal color. Right? By the way, I mean, I'm doing this without ever having explicitly mentioned it, and you have also not complained about this, but it's fine, right? There is a concept that has the scary name of eta reduction or eta equivalence. And if you ever hear that, it's actually a very simple principle which just has a very uninformative name. The point is you can write x equals y is exactly the case of equal color of x, y holds, right? So you can say, right, you're defining the operator equals, which has two arguments, to be the same as equal color applied to x and y. But you can also simply say that the functions are the same, right? The equality function is the same as this equality function. They're equal on, like, I mean, this is defined to be the same, right? This is and that's fine. It means the same thing. You can, like, whenever you have a declaration of the form f of x equals g of x anywhere, or with multiple arguments, right? Here we have something f of xy equals g of xy. Whenever you have anything like this, and there is no further occurrences of x and y somewhere in the g, right? I mean, like, if this is a complicated expression and it actually mentions the x and y in other places, then the situation is different. But if this is really just something which doesn't depend on x and y except this one occurrence here, then you can just write f equals g, right? And that's what's known as eta reduction, removing these arguments on both sides. If you don't find that convincing yet, it doesn't matter, right? I mean, it will become more understandable over time. I have no doubt. I don't think this is a blocker. Like, if you feel like this is somewhat mysterious, I think it's going to resolve itself. Okay. So yeah, we can derive equality as well. So we can actually, if we wanted to, we could go to color and say deriving show and eq. And then you have to know that if you want to, this is just syntax. If you want to derive multiple things, you have to put them, the type classes into parentheses and separate them with a comma. It's inspired a little bit by the fact that constraints, right? We saw type signatures that have constraints with a double arrow in the front. If you have more than one constraint, the constraints are also put in parentheses and separated by comma. I'm not sure how I can produce a good example of that. Let me first remove the error. So this is a duplicate instance definition again, because I have the instance down here, which I'll comment out. So if I, for example, define a function, just for the sake of example, foo of x, where I'm going to say I want to compare, let me say I want to do x equals x, and this is completely nonsensical, right? Show x equals show x, and is the logical and. Then the inferred type for this is this, right? It's I'm using the equals equals, which means that the type of x should be in the equality class, but I'm also using show on it, so the type of x should also be in the show class. And yeah, I mean, it's not a useful function, but it demonstrates the syntax for having multiple constraints on something. Okay, so let's see. Oh, did I already have this in? Yeah, so, okay, yeah, so I probably also want to define equality for cards. So let me also look for the definition of card and derive equality here as well. And then it will, this is going back to the one question we had earlier. Now it will complain that I don't have an equality for ranks, right? Cannot derive the equality for cards because we didn't actually define this one by hand, and here we have only one constructor. But if you have a constructor with arguments, right, then obviously the arguments also have to be equal for the whole thing to be equal. So you need to know what it means for two card colors to be equal and what it means for two ranks to be equal. So we need an equality instance for rank as well. And then the error message disappears. That's good. So, and then this expression here, for example, should also evaluate to true. Okay, now we can complete the actual score of the combination. So we can do well, actually, yeah. So it says again, it's probably helpful to define one more helper. So actually, let us define one more helper, and the helper will actually say whether the special case applies, whether we have a combination where everything is the same color. So let's call the same color combination, which is actually going from combination to bool. Okay, so same color combination. So we are having these two things again, pair, card 1, card 2. So a pair, or let me write out the pattern match first, and the triple, card 3. So here we want that the card color of card 1 is equal to the card color of card 2. And here we want that the card color of card 1 is equal to the card color of card 2, and that the card color of card 2 is equal to the card color of card 3. And I mean, this could be done in different ways, and Raphael will probably correctly suggest that we could perhaps, if we had something that would just collect all the cards in a list, and then we would have a function that checks whether all the elements in a list are equal, then we could write this more elegantly, and that's right? I mean, it's we'll get there, we'll learn that, and it's an additional exercise. You can see whether you can write this in a slightly more beautiful way then, right? I mean, there are often many different ways. But I would say sort of like the bread and butter way of doing pattern matching and doing all the cases, it may not always lead to the most elegant code, but it gets you there. It's often very systematic and it gets you to a result. And making things more beautiful subsequently is great. I mean, by all means, right? Always look at your code and see if you can simplify something. But it's also very good if you're already on safe ground, you already have something that works, you can improve on that rather than if you're still trying to get a problem solved for the very first time, right? Okay, good. So, yeah, I'm going to try to go on until roughly 3:45 because we started about 1/4 of an hour early, and I think the next step is effectively a big step towards introducing lists. So we're going to consider a stack of cards, and a stack of cards, you can think of it as a stack of cards placed on a table, right, is either empty, there is no card whatsoever, or if it's not empty, then you have a topmost card, and what's underneath is another stack. Does that make sense? And with this view, we can define it as a data type, right? We can define a card stack or just a stack and is either empty or there is a card on top. Let me call this on top. And then there is another stack underneath. And I said before that there is this thing with alphanumeric identifiers and symbolic identifiers are by default infix, and alphanumeric identifiers are by default prefix, and if you want to turn a symbolic identifier into a prefix identifier, you can enclose it in parentheses. You can also turn a textual identifier, an alphanumeric identifier, into an infix identifier by enclosing it in backticks. Or perhaps on top of, perhaps that's nicer. Yeah? Okay. And you can do that with anything, right? For example, there is a minimum function, min of 3 and 5 is giving you 3. But if you prefer, you can write 3 min 5. That's the same thing, okay? It always works with any, but only individual identifiers. You cannot put complicated expressions and suddenly say, oh, if this is an expression that actually expects 2 arguments, even though it's itself sort of made up of several function calls, I enclose the whole thing in backticks and then put it between 2 other things. That's too far. Only an individual identifier. But yeah, you can do it for functions, you can do it for constructors, you can even do it for types, but I think that's perhaps a little bit too much, but it works as well. Okay, so let's derive show. Perhaps we should even derive EQ, but we don't need EQ necessarily. Okay, so let's define functions on stacks. Let's start very simple and define a function that counts the number of cards in a stack. Right? We just want to know how many cards are there. So let's say stack size is going from stack to int. How many cases? 2, yeah, 1 for each constructor, right? Stack size empty, stack size of like card on top of stack. Let me write this out. Okay, so now there's one more thing. Like the whole, as I said, the main message of today is functions follow their data types, pattern matching, use one case per constructor. There's one more ingredient, right? There's something about the stack data type that we haven't had before. The stack data type is recursive. Right? The stack data type mentions itself. And this is an additional ingredient of what I call the standard design pattern. The standard design pattern in Haskell, the first and foremost design pattern is this: if you define a function via pattern matching, you by default have one case per constructor, and you recurse in the function where the data type is recursive. That means that you're trying to solve the empty case without further information, right? So what is the stack size of an empty stack? 0, yeah, okay. And here, you're not trying to solve this problem, but you're trying to you want to call stack size on stack. You want to do this, and you ask yourself, how does the stack size of this stack relate to the stack size of card on top of stack? Right? If I already know the stack size of the stack underneath, then what happens if I put 1 card on top? +1, yeah, perfect. Thank you. And that's it, right? Okay, so this is, and now you get a warning because card isn't actually used, but this is fine because the size of a stack doesn't need to know anything about the card, right? We don't actually need any further information about the card, only need to traverse the structure. Now, if there is anyone here, I just want to make a disclaimer, if there's anyone here who already knows a little bit more about Haskell, this isn't actually a good definition of stack size. It's like from a performance viewpoint. But the point is, this is nevertheless the most straightforward definition that follows the structure of the data type, and we'll see how you can, like we'll see in a moment, even still today, how you can in principle give a better definition here. But this is a secondary issue. Again, like you can, first thing is to get a solution that in principle is correct. If you can improve on it, even better, right? And this is the most straightforward, most design pattern following definition you can get. And you should always keep this in mind. In principle, follow the structure of the data type. So let's define more functions on stacks. We want to remove all cards of a given color from a stack of cards, keeping the others in the stack. We basically go through the stack and just like draw out all the cards that have one specific color, and then another stack is left. So let's remove color from stack. Takes a color, takes a stack, and returns another stack, right? So this is another one, card color. This is another one where you have multiple arguments, and I'm first introducing the arguments, and then I'm going to think about, right? I mean, now I have two arguments. Do I want to pattern match? What do I want to pattern match on? And I said very often it's the first thing, but not always, right? If you think about it, it's not really important which color I'm going to remove. It's not going to fundamentally change my strategy whether I want to remove the red cards or the blue cards. It's much more important whether the stack is already empty or not. So let's actually pattern match on the stack, right? So let's do empty, remove color from stack, color, and then card on top of stack. Okay? Can we solve this first problem already? If we want to remove all cards of the color from an empty stack, what is the resulting stack? Empty. Fantastic. And this is another, I mean, you will always say this is all trivial advice, but I'm really serious. And solve the simple cases first. I mean, there are some situations where you're really, really confident where you should take the opposite advice, because you're just wasting time with simple cases and you might not even know whether the complicated cases work. So this is like, there's always like different situations, different strategies. But while you're learning, right, allow yourself the potential feeling of success by doing the simple cases first, right? See whether you can get basically half the definition done before you tackle the potentially more complicated one. Okay, so here the strategy tells us what we want to do is we want to call the function recursively on stack, right? So we want to do something with the call of remove color from stack to some argument and stack, and often, but not always, but often this argument does not change. So you can, as a very first strategy, check whether you can make sense of this, right? Whether you can complete it using this. If I have already removed all the cards of that color from the substack, then what happens here? Now, what happens? Still not easy. But yeah. I need to know whether the card has that color or not, right? And now there are multiple options of doing that. I mean, perhaps to define a helper function again. Card has color. I mean, that's, again, I'm giving you these strategies because, I mean, you can be more, you can be like inline more things, but if you encounter anything even remotely difficult, split it off into a subproblem and see if you can solve it separately, right? Card has color. So how do we do this, right? We have a function for this. We don't really need to pattern match. This is one of the instances where we could use pattern matching again. It would be perfectly fine, right? We could theoretically even pattern match on all the colors and pattern match on all the possible cards with all the possible colors, and we would still get to the result, right? It would just not be a very nice way of getting to the result. But we can also just say, yeah, I mean, we have a function to extract the color from a card, which is called card color, and we want the card color of the card to be equal to this color, right? And again, I'm calling this, okay? Okay, and of course this is simple enough so that we could, in principle, inline it here. But even, okay, now if we have this function, now we need to do something depending on the result of this, right? Depending on the result of this. And how do we do this, right? And there are actually a number of different ways to do this. The one which I think in the end is most idiomatic is so-called guards. So you're basically saying card has, but this is extra syntax, card has color of color card, or let me actually just inline that. I think it's fine to just not use this extra definition, card color, card equals color. Then we want to remove it, right? So then we basically just call the function recursively, and we don't do anything else. And otherwise, we want to keep it. And that means that we also call the function recursively, but we put the card that we just had back on top of the result. Okay, and here we don't use the color. There are two other primary ways of doing this, right? So like this is perhaps the most magic, but because it uses special syntax and like really special syntax that you cannot always use because you can only do this sort of at the top level of a function definition. There is if then else as an alternative. So instead of this, I could have written remove color from stack color card on top of stack. And then if card color card equals color, then do one thing, else do another thing. That's the same, right? And actually the most fundamental thing would be to use a case. Sometimes you want to pattern match on the result of another expression without defining a completely new function. And that's where you can use case. You can say case, in this case, card color, card equals color. That's a Boolean, this thing. It doesn't actually need parentheses. Of, and a Boolean has two possible shapes, false and true, or true and false, doesn't matter which order, right? And that's actually the same thing as an if then else. People don't use it for Booleans, rarely, I see that rarely, but it's good to know, right? I mean, if then else is nothing magic whatsoever. It's only additional syntax that means exactly the same as a case analysis on a Boolean, which basically says, yeah, I mean, you either do this if the condition is true or you do that, okay? All right.
Is the otherwise a keyword?
That's a very good point. The question is the otherwise a keyword? No, I should have mentioned the otherwise. Yeah. Sorry for that. This was really an oversight. No, what you put here in the conditions of a guard is just any Boolean expression, and you can put arbitrarily many of them in sequence, and the first one that evaluates to true is the branch that is taken. And otherwise is not a keyword. Otherwise is defined in the prelude as an identifier that is just a different name for true. So it's really just something which will always evaluate to true. And you can even verify that by So this is just convention to use otherwise as the final catch-all case for for guards. It's usually only used there, but you could equally well just write true literally if you wanted to. Yeah. Thank you. That's something I should really have mentioned myself. Okay. Let's do one more, I think, and then stop. Sometimes we want to flip a stack, like we have a stack, and we basically just want to reverse the order of all the elements in the stack. And how would you do that? Like, how would you actually do that? If, like, I should have brought a stack of cards, but how would you do that operationally, right? I mean, you would take the topmost card and put it next to it, and then you would take the next card and put it next to it, and then you would take the next.
With the list again.
Yeah, no, I mean, this is the point. The stacks are lists. The reason why I'm doing this, this is exactly the definition of lists in Haskell, only that it doesn't have magic syntax, whereas lists have magic syntax. And that makes them a little bit more confusing. But if you understand this definition of stack, you understand the definition of lists, right? And reverse on list works exactly in the same way. But the strategy is what I just mentioned, right? You take, and this looks like, if you hear it like this, it sounds very stateful, and Haskell is basically a stateless language, right? We try to express everything as function and not with mutation. And I've just been saying, like, we're going to always take the topmost card and put it onto another stack. But there is very often a very simple way to model stateful operations in Haskell just as recursive functions. And we can apply that here. We can say, right, if we want to flip a stack or reverse a stack, it doesn't really matter, stack to stack. We are using this place next to our original stack as an additional ingredient, right? And we're building up the result stack here, right? So basically, we are operating on two stacks rather than just one. And this is the insight. This is the actual insight that you have to have, that this is sometimes a useful strategy to define a different function, which actually has an extra argument in this case. So we are actually going to call, if we want to reverse a stack, we're going to call reverse stack aux, like for auxiliary, but you can call it any other way, with an empty stack, because our second stack is initially empty, and the original stack. All right, and now I can define this separately. Stack to stack to stack. And this is my accumulated result. That's why I'm calling it ACK. And this is my stack, which I'm actually operating on and diminishing. And I have a result. And I'm not going to be so interested on the accumulator, because I'm just going to put things there. But I am interested in the stack that I'm sort of reducing. So this is the one that I'm going to pattern match on. Two cases, empty and card on top of stack. Okay, and now, right, if I'm done putting cards from one side to the other, then my stack is empty. And my accumulated stack is the result, right? Because everything is in reverse order. The topmost card is the lowest, right? So I can just return ACK. And in the other case, I want to call reverse stack aux again, right? Standard design principle on the stack. So I want to actually remove this card. But here the other argument changes, right? Because I'm removing it from this stack, and I'm putting it on top of this one. So I'm calling reverse stack aux with the card on top of the accumulated stack, but removed from the other one, right? And this is a very common principle that you very often, like if you want to model something like you're modifying a variable over time, you very often can simulate that in Haskell by recursive calls that just change the arguments, right? You're changing one stack to become smaller. That's why in the recursive call, this one gets smaller. And the other one to become larger. That's why in the recursive call, this one gets larger. And when you're all the way through, you can return the accumulated stack. And this actually works. Let's try it out. I mean, it's a little bit hard to come up with good example stacks because like creating cards is actually verbose. So, but let me just, like we had one example card already. Let me just use that. And then let's define another one, make card black rank 3 on top of empty. Oh, this is another thing, like I probably want on top of to be right associative, right? If I really use it as an infix operator, there's now an ambiguity whether this should be bracketed this way or bracketed the other way because it's an infix operator. One of the nice things is that in Haskell, if you define infix operators of any sort, you can also give them a priority, and you can say what their associativity should be. So I can say this should be right associative with priority 5. What the right priority is of course, something that I know by intuition. It's very difficult to know for you, right? But I mean, 5 is useful here. And you can see you're getting a stack back which has 3, like the black 3 on the top of the red 2. So it has flipped the 2 cards around. So it actually does work. Yes. So I think we should stop here. We've been going on for long enough. We'll continue tomorrow. But also you can, in principle, if you still have energy, perhaps after a short break, try to go on with this yourself. I mean, as I said, the solutions for the remaining, I think it's going up to 36 in here, but they are actually in the repository, in the reference branch. And then there is actually a full additional file called Day 1 Exercises, also in the repository, which does not build on, you don't have to necessarily complete all the 36 steps in the original file before starting here. I mean, many of these things should be doing with exactly the stuff that we have been doing here, perhaps, yeah, with a couple of exceptions we haven't really been discussing, maybe, and lists in very much detail yet, even though we've been mentioning both. But in principle, this is all doable. And Matthias and Joris wasn't there in the beginning. They're also going to stay around. And I'll briefly take like also a 5-minute break now, but I'll also be back. And in principle, if some of you are motivated, we can still go on at least until the podium discussion, which I have to attend, but not as a lecture, right? Just doing exercises. And then tomorrow, the room will be open all day as well, but we'll continue doing stuff at 1:30 again. Hopefully see you all back. Okay, any final questions? Okay, then thank you for now. All right, welcome to the second session of the beginner's track. So, are there, like, I mean, before my plan, okay, let me say, my plan for today is to do a little bit more in the day 1 file, which, and not everything, but a little bit more, which I think is sort of really necessary, and then there are a couple of steps at the end that we'll probably leave off. And then I have a day 2 part, which is primarily about I/O and Haskell. And we're going to try, and actually, if you've all been in Tom Ellis's talk this morning, then I think he did half my work for me, but I will nevertheless try to explain some of those things again. and we'll try to actually put it to use and see how sort of I/O works in Haskell, really. But before I just jump in again, are there any questions you have since yesterday that I should address before we start? No? Okay. I guess all the ones who have questions are already gone. No, I don't know. So the last thing that we did, it was to reverse this stack of cards, right? And perhaps it's actually a good introduction to look at that definition again and to actually let me scroll up yet a little bit more where we defined the stack. So this was one of our data type definitions of which we've seen a lot yesterday, right? A stack has one of two shapes, like the two constructors. One is called empty and one is called on top of. And on top of because it has these backticks where we can write it in between its arguments, but it works exactly as if we would write it without the backticks before, right? So empty is a constructor that has no arguments, representing an empty stack of cards. And on top of is a constructor that takes one card and another stack. And the idea is that the card is sort of the topmost element of the stack of cards, and the stack argument is the sort of one card smaller stack which is underneath, right? And then this declaration, which I did not really explain, is sort of like for operator priorities, right? As I said, in Haskell you can define your own infix operators. And that means you can also actually give them priorities and associativity, and you don't actually have to like learn a fixed operator table and their associativity. And one useful thing to perhaps know is that there is another one of these GHCi commands, which also works in the eval plugin, which is this :i command. And somewhat inconsistently for :i, you always use a single identifier and you don't even have to put operator names into parentheses. I mean, so this is sort of like, I think, a little bit inconsistently. Perhaps it now works if you put parentheses around. In the old days it didn't. Let me actually just try this briefly. Yeah, I think it actually works now. Okay, so then it's probably better if I do this. And then you get some information about where the identifier actually is coming from and how it's defined. So actually, I mean, this is not my main point here in this case, but you can see that there is a class num and it contains this operator definition of this type signature, and it actually shows which internal GHC module this is originally defined in, but it's imported via the prelude. But in particular, it also actually shows you the priority and the associativity of that operator. So this is a good way to find out operator priorities if you're uncertain about them. You just look them up with :i, right? So similarly for, I don't know, if you want to like look at the priority for multiplication, you see that that one is 7, right? And so you can do that for effectively all the operators. And we saw this list append operator, but we haven't really seen lists yet which has priority 5. So yeah, so you always get this information out effectively. Okay. So then reversing was this idea that we introduce a helper function and then we basically work with two stacks of cards, and we are traversing the original stack, which was the right one, right? Because we passed this on as the second argument to reverse stack augs. And the left one is, which I call sort of the accumulating stack, is initially empty. And if eventually the right one is empty, then we hope that on our left accumulating stack, we have the reversed stack, and then we just return that. And if we have a card on top of a stack, then we simply remove it from the stack by calling the function recursively with the stack one element smaller and put it instead on the accumulating stack. And that will then gradually flip the order of the cards one by one. And we looked at this example, which is a little bit tricky to read, but we've seen essentially that it works. Okay, So let's write more functions on stacks and thereby introduce a number of other data types. So in particular, a data type that I think I also briefly mentioned yesterday already, but which is very important in practice, is the maybe data type. This is one which exists already, right? You have it available via the prelude, but there is nothing magic about it whatsoever. It can be defined as a data type declaration just as this. The only thing that we haven't really seen so far, or at least not very explicitly seen so far, is that data types can also have parameters. And so a maybe of A can be applied to, like this A can be any other data type, right? So you can transform one data type into a new data type, which essentially has all the elements of the data type you're transforming plus an extra one, right? That's the idea of maybe. And this extra element is called nothing. That's that shape. And if it's one of the old elements, then you have to put just in front because you have to tell the shapes apart. You always have to use a constructor, right? And this is, there are different views of maybe, right? The most common view is it gives you a way to denote some exceptional situation, that like a means of denoting failure, right? You can say like this, I cannot actually properly do this. But you're doing that in a very disciplined way because it changes the type and it indicates to the user that, like, I mean, now you're getting from somewhere, you're not getting an int, but you're getting a maybe int, so you have to be prepared for the fact that it might not actually be an int, but it could be nothing, and you have to, like, tell very explicitly subsequently what you're going to do with it, right? Another way to look at maybe is sort of as a container which has exactly 0 or 1 elements in it. That is sometimes also a helpful view. Of course, it's not a contradictory view, but just a slightly different perspective, and sometimes that also helps. Okay. If you really, really want to deal with lots of different error situations, then maybe is not a great type because you typically want to have reasons for your errors, and nothing does not really tell you much. So if you, like, imagine you have your long-running piece of code and you're running your computation for 2 hours, and then in the end the result is nothing, then that is not particularly satisfactory. You would rather perhaps have had some information about what actually went wrong, right? But in simple cases, it is exactly the right thing. So here, the idea is we want to find the highest valued card in a stack, right? And we had these different values associated with cards. But since stacks can be empty, right, it is not clear that we can find a highest valued card. In fact, it is relatively easy to decide whether we can find one, because, I mean, we cannot find one exactly if the stack is empty. But nevertheless, I mean, we have to be somehow precise, right? Or we want to be somehow precise. And in Haskell, we like really try to avoid writing functions that are partial. That's the typical terminology. Functions that are not defined for all inputs. You typically try to tweak the types in such a way that ideally you make them always work. And you have, in general, you have 2 possibilities here. You could either require, which would actually be even better, you could either require upfront that the stack that you're feeding in is somehow not empty, right? Like use a different data structure perhaps for non-empty stacks. Then you could always guarantee that you find the highest valued card in it. Or you can say on the output side that you're not sure whether you can come up with one, which is the approach that we're taking here. Okay? But I said already that we can basically make that decision up front. So basically the best way, I think, to do this, highest valued card stack to maybe card, is to do a pattern match here on the stack and say empty, or we have a card which is on top of a stack. And in both those cases, we have to do something. right? We have to put something on the right-hand side. And this case we can already solve, right? Because the result is nothing, exactly. And this we can also partially solve, actually, because we have to produce a maybe card, and we know which of the two constructors of maybe we need, namely, what did you say, sorry? Just, yeah, the other thing is an argument. That's more problematic. What the argument should be is the big question, but we can put just, right? And again, like simple example, so it's relatively difficult to motivate the usefulness of this, but again, you can see this needs a maybe card. It indicates you should think about, the same way you should think about on the input side, if there is an input which is structured, can I do pattern matching in order to get further? If you have a structured output type, something like maybe card, you should ask, is there a constructor of the maybe type that I can already apply, right? That I already know must be the right one. And in this case, I can say just apply to something and push the hole down. And now I have a hole which is just of type card, right? Now, in order to find which card this is, I have to do real work, right? But the point is now I'm in a situation where I know I have at least one card, and now I can apply the same idea, fundamentally same idea as we have done for reverse, only that in this case our accumulated result is not a stack, but it is the minimum, or the is it minimum? No, the maximum valued card, the highest valued card. So basically the current maximum value card that we have seen, right? And so we're basically doing exactly the same. We're calling a helper function, highest valued card aux, with an accumulator, which is initially the card that we have seen as the very first card, and then the stack. And this we're going to have to write. So card to stack. And this is now to card, right? This is no longer partial. And this takes the accumulated, the currently minimal card. And now we're doing, let me again be slow, right? Let's first introduce the names for the arguments. We have this situation, and we're doing pattern match on the stack, right? Just as usual, right? This thing is always a slightly difficult creative step that you're saying, oh, I can solve the problem more easily by introducing a helper function that actually takes an additional argument, right? That is a little bit of creative insight that you actually need in order to make the problem simple to use. But from here, it's really straightforward. You're doing like standard design principle. You do pattern match on the stack. You have two cases, one for empty, one for on top of. And what was the additional ingredient that we had when we were operating on a recursive data type? What was the additional idea? We want to recurse in the function as well, right? Ideally, right here, we want to call highest valued card aux on stack, right, with some suitable argument. So that is something that we want to do, some argument for the accumulator and on the rest of the stack. So let's first try to solve the simple problem again. Like if we have accumulated a card and the stack is now empty, then what is our minimum, or maximum, sorry, I'm always saying this wrong. Oh, nothing would be bad.
You have to define the output as a maybe call.
Yeah, we've done that here. Yeah, but now we are in a situation where we have at least one card and we initialized our accumulator with that card, right? And so here we've now like went through the whole stack, and we have that as the current minimum card. So that is also the final minimum card, right? So that's actually also typical for the situation where you have an accumulator. You see that in the top line of the buffer right now for reverse stack, that you're saying, like in the empty case, you're just returning the accumulator, the final accumulator. Here we're doing the same. That is the usual thing. Sometimes you do a little bit of final post-processing as well. It happens that there are situations where you say, oh, well, yeah. And then in the very end, I take the accumulator and do this one extra thing to it. But the most common case is actually that you just return it, that's already the final result you're interested in. And then in the other case, right, I mean, first of all, perhaps in the recursive call, we should figure out what is the new accumulator, right? The idea is we are going through the stack. We're having the current maximum, sorry, why am I saying minimum? The current maximum card in our hand next to the stack. And we're now looking at the topmost card of the stack that we're going through. What do we have to do with these two cards? Yes?
We have two cases. Either the accumulator is bigger than the call,
Mm-hmm.
we keep the accumulator, or the call is bigger than the accumulator, then we replace the accumulator with the call.
Good.
What is if it's the same?
Then we have to make a decision, but given that as far as Haskell is concerned, two cards, at the moment, right? We have this card value, but at the moment, two cards only have the same value if they're actually completely identical as far as Haskell is concerned. So there's no further identity, so it does in practice not matter. Yeah. But you're right. The question is valid. In other situations, you might have to make a decision. Like, do you keep the first one of several similar cards, or do you keep the last one, or do you disallow this completely? Or yeah, it's a good question. But yeah, we are basically just going to take any one. For example, let's try to take the first, even though it shouldn't matter, right? So now we have this function, what was it called? Card value, I think. Was it card value? Or value card? Or no, card score, I think. Is it card score? Or score card? Score card. Oh, last option. That's the one that we want to use in order to compare, right? So there are actually, again, multiple options. We could actually write some sort of minimal card function that selects the minimal card between two cards based on this. That would perhaps even be slightly cleaner. But we can also just do this in an if then else, or in a guard, or in a case expression just here where we are. So here I'll basically just check using a guard again. I'm going to say, is the score card of the card, is that greater than, strictly greater than, the score card of the accumulator? And then I'm going to do something, and otherwise I'm also going to do something. I probably want to call the function recursively in both these cases. And I think you already mentioned what we should be doing. So what should we do if the score of the card is greater than the score of the accumulator?
We replace basically the accumulator with the call.
Then, exactly, then we basically use the card here as the new accumulator and disregard the old one. And in the other case, we keep the accumulator and we disregard the card. And actually, if you think about it, we don't need to do anything here, right? The recursive call already is what we want. So There's nothing else that we need to do. Oh, okay. And we really need a better example list in order to be able to, so let me extract this. Even though it's only a 2-element stack, it's still not really satisfactory. Let me say example stack here of type stack. And then let me try here to call highest valued card on the example stack. And that is giving me just, right, of the black card of rank 3. And the black cards were very highly scored, so this is plausible. That I think the other one in the example stack was red, and that would be of much lower value, right? And we get a just because it was a successful result. We can also try to see whether highest valued card on an empty stack correctly produces nothing, and it does, okay? So, any questions? Does it, the maybe, the parameterization of the maybe type and so, that makes sense? Yeah? Works exactly as before in principle, okay. Because we're now going to get to actual lists, right? We have been, we know that they exist and so on. We have been mentioning them briefly before already. But the concept of stacks that we've seen is effectively what Haskell lists are. The only two differences of Haskell lists and the stacks that we've seen are Haskell lists have magic syntax. They are like, and this is really something that you could not define yourself. Like they function exactly as normal data types, but with a syntax which is like different than anything that you could have defined yourself. So the data type name is effectively these square brackets around the parameter, right? And that's something that you could never define yourself, something like with two symbols on the left and right and the parameter in the middle. But for lists, that is how it works. And there actually still is a prefix way to write lists. I mean, that's mostly a curiosity, but you need this sometimes for defining instances. So, so like whether you write, you can, I can say list is a list of integers, and right, or I can say list is a list of integers. This means the same thing. Like the first one is idiomatic, the second one is not. But sometimes you want to really like talk again, like in other situations as well. You want to talk effectively about the type constructor, as it's sometimes called, without its argument, right? And then you can. Then it's just the bracket open, bracket closed. And anyway, so that's the type name. Then you have two constructors. And this is the one that is corresponding to our empty, right? And that is written just as bracket open, bracket closed. And then you have a constructor that corresponds to our on top of, and that is written using an infix colon. And this one is pronounced cons. And it has two arguments. This one is what's corresponding to our card, right? That's the top element or the first element of the list. And this is the recursive occurrence. This is corresponding to our recursive occurrence of stack. So this is the rest of the list. Okay, so it's exactly the same structure as lists. And indeed, like there is a direct correspondence between our stack type and a list of cards. So one-to-one correspondence. And we can make that very explicit by writing conversion functions that actually like map one to the other, right? Stack to list, let's just write that briefly so to make it absolutely clear. So if we have an empty stack, then it corresponds to the empty list. And if we have a card which is on top of more cards, then it corresponds to card cons. And again, standard design pattern, right? Not just card cons cards, because cards are still a stack. We have to call the function recursively, right? It just follows the pattern. So stack to list of cards. All right? Makes sense? And similarly, the other way around, list to stack. We start with a list of cards. We go to a stack. Same thing. We have two cases to consider, the one where we have an empty list and the one where we have a non-empty list, which is constructed using the cons operator. And in the case of the empty list, we now produce empty. And in the case of the cons, we now produce on top of. And we put the card on top. And we recursively call list to stack on cards. And that's it. And you can relatively easily see that these are mutual inverses and that there is an exact one-to-one correspondence. Often called that these two types are isomorphic, right? So you have a function going from one type to the other and a function going from the other type to the first, and you can compose them in both directions, and if you compose them, it's the identity function. And, does that make sense? Okay. So the next one I'm going to skip in order to save us some time. That is basically just practicing with the list syntax by redefining reverse yet again on lists. I mean, we have had flip stack. That was our function that we started with today, like the reverse. We actually called it reverse stack yesterday, but that's the function that is meant in that step. That reverses an entire stack. The same function exists on lists because this function makes no assumptions that we're actually having a stack of cards. It just treats the elements as black boxes effectively. I mean, it just passes them on. So it works in exactly, we could exactly in the same way define it on lists of arbitrary element type. And this function exists in the library. And it is called reverse, like very surprising. And we can try that out on a number of different things, just rather than writing it. We can just say, like, if we have a list of numbers, and this is actually another thing which is magic syntax about lists. You can write lists conveniently in this syntax, but what it means, whenever you write this syntax, is actually successive applications of cons onto the empty list. So this syntax that I've just used for this 1, 2, 3 list is exactly the same as saying 1 cons, and then 2 cons, and then 3 cons, the empty list. The parentheses are not really necessary here either, because the cons operator, again, is right associative, but just for emphasis, right, that is the internal interpretation. And whenever you use this syntax, it's automatically desugar to that. And similarly, like the show instance is also using this more convenient syntax. But that's always how to think about lists, right? And as I said, I mean, this works really, I mean, if you look at the type of reverse, it is one of those parametrically polymorphic types. So it means you can choose any list of any element type. You'll get a list of the same element type out, but it really works for whatever list you put in. There is absolutely no limit. There are no constraints on this A, right? So I can reverse a list of, let's say, Booleans, false, true, true. I can reverse a list of, let's say, floating point numbers. I can reverse a list of, what else did we have? Just colors, for example, yellow, red, right? I mean, it works for whatever I like. I can even reverse a list of functions if all the functions have the same type. The problem with reversing a list of functions in this setting is that functions are one of the types that don't have a show instance at all. Right? So if, for example, I have a function such as plus, and I just type the function and nothing else, actually, this is a weird corner case of Haskell why it specifically complains about integer to integer to integer. That I don't want to go into that today. But nevertheless, I mean, it effectively says, look, plus is an operator on two numbers, right? And I don't have a show instance for that. I don't know why, or I don't know how to print such a function. But you can, in principle, you can like you can write a function. You can define a list of list of integer operators, something like that. And let's use int rather than integer. And say, well, let's let that contain plus and minus and perhaps times. Just so, and this is a type correct definition, right? And I can also say reversed list of integer operators is reverse of list of integer operators. And that is still a type correct definition, which has the same type. I mean, doesn't complain about it. Simply just showing it wouldn't be particularly enlightening because the show instance doesn't exist. But type checks and you can work with it, right? We can even use it as an example in a moment. Okay? Let us write another function on lists, though, just to get a bit more practice, also with the list syntax. And that is append. I mean, this is actually a function that exists as an operator definition, plus plus, but in order to make it slightly less confusing, I'm actually going to define it as append for the time being, because the operator version, I think, is a little bit, there's too many symbols next to each other that makes the makes it slightly confusing. So we get two lists, and we want to create a list that contains both lists, right? I mean, in order. Like we have 1, 2, 3 in one list, we have 4, 5, 6 in the other. We want to get the list 1, 2, 3, 4, 5, 6. The same we could do with our lists of cards, right? If we have one stack and another stack, we essentially want to put one stack on top of the other, the whole stack, right? So here again, you have a situation where you have two structured inputs and you have to make a decision which of the two you want to pattern match on. And I guess you could try to pattern match on the second, but you would quickly discover that you're not getting very far. The intuition why pattern matching on the first is better is that lists they're asymmetric data structures, just like our stacks have been asymmetric data structures. You only have access to the top or to the left, depending on how you want to look at it. But you cannot really look at the end, right? And therefore, everything, like if you want to destructure something and restructure something, it is better to look at the beginning of things. And the beginning of the final combined list will be the beginning of the first list. So that's more interesting. So let's make the two cases here. And then standard design pattern also tells us, right? Always keep this in mind, not just two cases, one for the empty list, one for the other, but recurs where the data type is recursive. So we want to call append on XS and something, right? So we want here to call append on XS and something. And then possibly do something with the result of that. But let's first solve the simple case. If we want to append the empty list to another list,
The other list, why?
then the other list, right? Yeah, then it's just the other list. Okay. And now, I mean, there are multiple strategies of thinking that can lead to success. But again, this is what I just said about the maybe situation as well. You can always look at if you have a structured result type, in this case it's a list, and you append x, cons xs to ys, can you already say which constructor we must use for the result? Yeah, I mean, you probably mean the right thing. I mean, you can already say that the resulting list is not empty, right? Mm-hmm. Yeah. So therefore, it must be cons of something, right? It must be. And so we know that it must be cons, and we probably don't want to make the recursive call to the left of the cons. And we also actually know what the first argument of that cons is, namely? X, yeah, okay. All right, and then given that we want to make the rest the recursive call anyway, I mean, we only have to figure out what goes here and what goes here. Just y's, right? The same y's. So we append a non-empty list to y's by just like producing the first element and then appending the rest of the list to y's. And that's it. We can try that out. Append.
The reason that you want to pattern match on the first list and not on the second is that just that the first list is on the left, like if you would like to append them in the other direction.
Yeah, if you wanted to flip the order, like, yeah, sure. If you wanted to have the second list before the first in the end, then you would need to pattern match differently, yeah. That is absolutely true. Yeah, so this works as expected. And in fact, yeah, I mean, this function exists in the library, and it's called ++, right? So you can do 1, 2, 3, ++, 4, 5, 6. And that's the same thing. And we could have defined this as ++, but the point is then, yeah, I mean, either you define this prefix or you define it infix, and then you have like all these brackets and ++, and I think it is slightly more readable, the structure of the definition, if you don't do it. But it's possible. There's nothing magic about that one. ++ we have seen before also as the string concatenation operator, and this is really true. I mean, strings are actually in Haskell, as I said yesterday already, they are just lists of characters, and they have yet another special syntax that is the one with these double quotes. But actually, all three of these versions are equal to each other. So individual characters can be enclosed in single quotes and are then of type character, C-H-A-R. So if we like ask what is the type of this, we'll get it's a character. And lists of character and string are actually synonyms. They are type aliases for each other. If you ask with :I, what is string? Give me information about string. Ignore the first line. That one is actually like difficult to explain at the moment. The second line is the actual definition. And this type keyword here means it's a type synonym, like one thing is defined to be just an abbreviation for the other, and string and list of character are interchangeable. You can use like string and list of character. Wherever you can use one, you can also use the other. And it's fundamentally different from a data type, right? A data type introduces a new type that is different from all the types that have been there before. It gives new names to shapes and so on. It's completely distinguished. Type aliases or type synonyms are not introducing new data types. They're simply introducing a new name for an already existing data type that you can use alternatively. Okay. Good. Okay. So, and yeah, because strings are lists of characters, I mean, all these three versions, including the one with the explicit conses, are actually the same. Okay? Oops. This is, I think, the eval plugin sometimes gets confused with where exactly it should insert the results. Yeah. But all these three are giving the same result. Okay. Now we had a function that removed all cards of a given color from a stack, right? And we can actually do something similar on lists and generalize it as well by saying, well, we actually want to remove all elements or keep all elements. Filter actually keeps all elements that satisfy a particular property. And that's a very general and very important function on lists. And this is a so-called higher order function because it takes another function as an argument. So this is the type signature of filter. Filter takes a function that takes something to a bool, and then it takes a list that must be containing the same somethings, and then it produces yet another, usually shorter list that contains such somethings, right? Let me call this filter list here so that it doesn't clash with the predefined version. And how do we abstract over functions? Just in the same way. This is like something where the sort of the low overhead, the low syntactic overhead of the function application syntax in Haskell also really comes in handy. So we can just give a name to the function argument. Let's call it P for predicate, just as we can give a name to any other argument. And then the list argument, let's call that access. And now functions you cannot pattern match on functions. Functions are sort of like integers. I said integers are a little bit weird and strings are a little bit weird, or well, strings not actually, but characters are a little bit weird, and so there are some built-in data types that are a bit weird, and functions are still, I mean, they are very, very powerful and very first class, but they are not data types. They don't have constructor names that you can pattern match on. The only thing you can do with a function is apply it, right, to an argument, possibly multiple times. So here, if you have this situation, the thing you want to pattern match on is again the list, right? There's no option to pattern match on the function. So let's make two cases for this. And now, if we have an empty list, then the result is easy, right? If we have an empty list to start with, then there's nothing further we could possibly drop. The only thing we can meaningfully return is the empty list. And here, in this case, right, we again have two choices, right? If we go back to the, where was the remove color from stack function, right? It follows more or less this structure, right? We are checking whether the condition holds, and then either we're keeping it or we're not keeping it. In this case, I said, now we want to keep all the elements that satisfy this property. So we have to, for example, again, use guards. And the interesting case we're interested in is whether P of X holds, right? I see this very often somehow for beginners, that they somehow want to treat Boolean special, so that, I mean, I see very often beginners writing something like P of X equals true, right? I mean, it's slightly unidiomatic, right? I mean, it's completely redundant to compare something to true. The P of X already evaluates to a Boolean, which is either true or false. Explicitly comparing that with true is not doing anything further, right? So this thing here will result in a Boolean, and this branch will apply if that Boolean is true. And if the Boolean is true, then we're keeping the X, similar to the second case here, right? X cons filter list P of X's. And otherwise, we're not keeping the X. We're simply calling filter list P of X's. And now we get a warning that the P is not used in the first case, and that is okay. We really don't need it. So we can replace it with an underscore. And now we can use our filter list on some examples. Yes?
So what do you gain by replacing P with underscore. Is that like easier to compiler?
No, it's not easier to the compiler. The compiler gives a warning because if you're introducing a name and then you're not using it, it may indicate a potential mistake that you've made a type or you meant to use the name somewhere or you've just forgotten about it. So it's a valid concern, and that's what, it's not an error, it's a warning. And I think I said that yesterday as well. Like, either you recognize that it is actually something that you did wrong and you fix it, or you kind of acknowledge that, no, I really don't want to use it. And one way, or the easiest way to acknowledge that is to replace it with a wildcard pattern that doesn't introduce a name in the first place, and then the warning goes away. But operationally, this produces exactly the same code. I mean, it's only sort of like a concern that, yeah, it basically gives you the opportunity to check your code once more and to say like, yeah, no, this is right. I really don't need that. I don't want.
It's because it doesn't really matter what it is, because
right.
you can ignore it.
Exactly. Yeah, we get the empty list independently of whatever function. We don't need it in that case. Yeah. Right. Okay. So. Actually, yeah, let's use it, and perhaps let's use it at first to actually like re-express the remove color function, but on a list of cards. So I should be able to write filter list and then something and then cards, right? And now I have to put a function from card to bool here. And now if I really want to reproduce this function, I want to check, right? I mean, this is a function that goes from a card to a boolean. I want to check whether the card color of this card is unequal to oh, well, actually, I should give the color argument, right? The color that I want to remove. Card color, let's call this color. Yeah, so I want to check whether whether the card color of this card is unequal to color, because like I'm keeping the elements that pass the test and I want to remove the ones that have that color, so I want to keep it if it doesn't have that color. So I need this function that basically says, given a card, check whether card color of that card is not equal to color. Now I could define a helper function for this, right? Introduce a new name that checks that, right? I mean, sort of like, but it feels tedious to like define yet another function for this. And so one thing that we haven't yet seen, but I think it is by now, when Haskell was first introduced, like was one of the first languages that had this, but these days it's a very common feature, so I'm sure that many of you have seen this before anyway. You can introduce an anonymous function as a so-called lambda term without explicitly giving it a name. And the syntax in Haskell for this is that you write a backslash, and then you give a name to the argument. In this case, the argument is a single card. And then actually we can place another hole here. And then we have to produce the Boolean, right, the result of that function. But in order to produce that Boolean, we now have relevant bindings include, if I can actually manage to scroll here, we now actually have the card in scope, right, the card of type card. And we can just write what we wanted, card color of card is not equal to color. Okay, you have to know that not equal is available using this operator. Another way to write that is also to check for equality and then negate the result using not, which is just a function from Boolean to Boolean, which is also in the library, right? That's equally fine. Okay, and that works. There are many things you can do with filter, and in particular, like these higher order functions, they're the main motivation, I think, for lambda terms, because you often have situations where you want to do something like you could, for example, check in a given list, check whether, I don't know, x is greater than 2, right? oops, not like this. Like given an x is x greater than 2. And then if I have 1, 3, 7, minus 4, 5, 4, 3, or something like that, then I get all the elements out that are greater than 2. Right? And there are many such things that you can do. And in fact, there's another syntactic peculiarity. I'm sorry that, I could also omit all of them, but these are really often and widely used, so I want to introduce them to you. So there is a thing in Haskell that is called operator sections, and that is just special syntax for such lambda terms that effectively partially apply an operator. So if you say, right, so something like lambda x greater 2, you can actually write that more compactly as this. And this is like not just the operator enclosed in parentheses, but the operator with either the left or the right argument next to it and then enclosed in parentheses. And it means kind of the obvious thing, right? Exactly the same thing as before, but there's also the opposite, right? You can also check 2 greater, which is checking whether 2 is greater than each of these elements, so it'll keep the ones that are actually smaller than 2, strictly smaller than 2, and that expands to lambda x 2 greater x, right? 1, 3, 7, minus 4, 3. Oops, not 7 minus 4. Okay? Yeah? Many things, but yeah. This is very common, right? Also writing something like parenthesis open plus 1, parenthesis close for the function that increments something by 1, or parenthesis open times 2, parenthesis close for the function that doubles something, right? So that's a common thing, you see. Okay. All right. I think this is, these are the final 2 that I want to do before I move on to I/O. So every card has a matching card. So this is actually another simple exercise in a way, to something like, doesn't like introduce a really new concept. It's just repeating old concepts essentially. So we want, every card has a matching card. The matching card is the one of the same color, so that the ranks add up to 4. Let's define a function that computes the matching card for a given card. So we want to define matching card from card to card. And cards had colors and ranks, right? And the resulting card has the same color, right? But it has a different rank. So we have to compute the matching rank of the rank, and that's easiest done with a helper function again. Matching rank to rank. And here you actually, again, I guess you have at least 2 obvious options. One is to just do pattern matching, right? And actually it's not too bad. You just say rank 1 is rank 3 because 1 plus 3 is 4. Rank 2 is matching with rank 2 because 2 plus 2 is 4. And rank 3 goes to rank 1 because 3 plus 1 is 4. You could also say, well, take this specification more literally and actually say, well, go to the score, then subtract something from 4 and then convert back from the score to a rank. But because we don't have this convert back from a score to a rank function available, it would actually end up more complicated than this one, right? So, but, okay. Yeah, so now we have a matching card function. And now we want to compute from a stack of cards, the stack of cards where every card has been replaced by its matching card. And well, we can do that either for the original stack type, or we can do that for our list of cards type. It doesn't really matter. Which one do you prefer? Any preference?
The second one.
The list? The list? Okay. Yeah, so matching cards. Let's go from a list of cards to a list of cards. We do pattern matching. I do that in one step. I hope that is already effectively clear. And we keep in mind that we probably want to call matching cards recursively in the second case. Now, if you want to replace every card with its matching card, then the length of the list stays the same, right? So an empty list again goes to an empty list, and a non-empty list goes to a non-empty list. So that again means in the second case, we know we want the cons operator here, and basically we only have to consider what is actually this first element here, and that is the matching card of card, right? All right, now we can try this out. Matching cards of example, oh, I think I only have example stack, but fortunately, we have also defined stack to list, right? So I can turn the example stack to a list using stack to list and then call matching cards. And if I also add again what stack to list example stack is, oh, now again it gets confused. Let me do this again. Evaluate. Then you can see that for red rank 2, the matching card is exactly itself, because same color and 2 matches 2. But for the black rank 3 card, we get the black rank 1 card. Yeah, okay. And this is another extremely, probably even the more common, or like even the more important, perhaps one of the single most important functions at all, right? Applying a function uniformly over all elements of a data structure. This is called map, and it's extremely common, right? And this is an instance what we've done, right, where we've applied the matching card function over each of these elements. So in principle, we can just abstract over this. We can really basically just copy the function definition and modify it into something which we then want to call map list. And we want to abstract over this, like here, the recursive call will also be a map list. We want to abstract over this matching card function. We want to give it a name such as f, because we don't know anymore really upfront what kind of function it will be, so it doesn't really make sense to give it a very descriptive name, because it can be nearly anything. And then we want to make that another argument of the function map list. So it becomes an argument here and an argument there and an argument in the recursive call. And that's basically it. Except that, yeah, because the type signature does not yet mention the function. But actually, we can use type inference in this case. We can just let the type infer. It doesn't choose the type variables that I would have chosen, but the choice of type variables doesn't matter all that much. Right? It's a function. Yeah, let me change them around, right? From A to B, like if we get a function from A to B, then we want a list of A's, and we turn that into a list of B's, right? And again, we don't actually need the function in the first case. And that's map. And that is available under the name of map, right? So you can do map, and then, yeah, and this is where like lambda expressions or sections again come in handy. I mean, something like map plus 1 of 135 gives you 246, or map of times 2 of 135 gives you 2610, and so on, right? And it doesn't have to, and now it does not work just on lists of numbers. It works again, it's parametrically polymorphic. It works on everything, right? And so here, this is actually a way of like bringing our list of functions, what was it called? Integer operators or something like that? List of integer operators, which was a list of ints. We can now actually do something with that. So we can take map something over list of integer operators. And so we get an operator or a function, which is a function, and then we apply it, let's say, to 3 and 3, or to 3 and 4. And now, what were the functions in our list? Right, the first function was plus, so we get 3 plus 4 is 7. The second function was minus, so we get 3 minus 4 is minus 1. And the third function was times, so we get 3 times 4 is 12, right? Just all works. Okay, good. This is where I would leave the day 1 file behind, and I would switch over to the day 2 file. And so basically, I'm going to go from the, I'm already here in the day 2 directory. I'm now in the day 2 directory that's in the repository, but there's not very much in those. It's a bit different than in the other file, because I thought, yeah, I mean, I wasn't quite sure how much time we would have, and I want to spontaneously adapt. But the rough plan is to talk about the way how I/O works at all, and to use random numbers as an initial example, and then to do a little bit of screen input-output as another example, and perhaps write a very simple interactive number guessing game. Nothing that will be very interesting or spectacular, but something that perhaps can be used to highlight some common structures, and that will nevertheless sort of answer the general question of how you work with I/O, and how also the sort of the functional language interacts with all of this. And again, like, yeah, I mean, Tom in his talk on the very first slide this morning, he gave these examples with referential transparency and why I/O doesn't work like in other languages, because you want to be able to have certain properties hold. And I think that's a very good way to phrase it. I mean, so the main motivation is indeed something like, if we had a number, I mean, we have, like in the end, let me just say, I mean, the function in Haskell that computes a random number will be called something like this. And this is another like data type that we haven't really seen here, is a pair data type. But you could equally imagine that it's just taking 2 integer arguments. I mean, it doesn't really matter. It's actually a weird choice. Why of all things is not currying not used for this function? I don't really know. Probably in order to like give a little bit of a hint that this is supposed to denote a range, right? But it's only an optical hint. So this will give you a random integer between 1 and 6, right? That's the idea here. Let's, for the time being, just assume that this wasn't something with I/O, but it was just a normal function somehow, and we could say, let R be random R, then I'm not mentioning the I/O, a random number between 1 and 6, and then you want to do something like R plus R. Now, does this, right? I mean, again, this doesn't work in Haskell, but the big question, or the big design problem here, why the designers didn't want it to work, is, does this compute one random number and then add it to itself? or does it compute 2 random numbers and add the results of them, right? And most languages answer that in the way by saying, oh yeah, this computes 1 random number, right? But then they are not referentially transparent, which is what Tom said, because in Haskell you want to have the reasoning property that you can always inline and outline common sub-expressions. And if you write a let like this, you should be able to say it is just blindly the same as this, always, right? But now you cannot really make a distinction between whether you want 1 random number or 2. There is simply no, right? But you want to make a distinction between these 2 things. So you need something more. You need to make a difference between sort of like, yeah, whether you're talking about the concept of creating a random number and when you actually want to run that concept and execute that concept and when you want to actually get the result. And this is the general idea why in Haskell I/O, anything that why random is in I/O is a slightly independent question, but anything that sort of is non-deterministic, interacts with the outside world, or in practice, the way that random number generators are implemented is they initialize themselves via something like a timer or something, and then they maintain some state, some internal state, and that state changes. And so that has to be maintained somewhere. So it's not actually a function that is pure in the sense that if you put the same range in, you'll always get the same result out. And that has to be tagged in the type system, right? So in Haskell, you have a type I/O, and an I/O is a parameterized type, and an I/O int is basically a description of a procedure that if you execute it, it will do something, right? Can do all sorts of things, and then in the end come up with an integer. And that doesn't always have to be the same integer, right? And then it's a data type like any other. There are specific operations that you can use to build larger I/O actions from individual I/O actions, where you can say, oh yeah, and now I actually want to do this, and then that, and then that. And you'll see that, right? So that's there are specific operators that operate on I/O actions. But for the time being, in order to get our random number generator, we have to leave the prelude behind, and we have to import a module that is called system random. And I'll at the moment get a warning that this import is redundant because I'm not yet using anything from it. And also, this is one of the reasons why I put it into a different package. We now need external package dependencies. Let's briefly have another look at the Cabal file for this one. So here in the build depends section, previously in day 1, we only had base. And I now added 2 more packages, containers and random. Random is the one that gives us the random numbers. I don't think we'll actually end up using containers. I was just putting it as in case we are using it, it's already there. But it's not the one that we are likely to need. And yeah, and if we have that, then we can actually start asking about what is the type of random RIO. And we can see if we can read that. This is already scary, but but that's also why I'm explaining it, so that you can learn to read such type signatures, even if they mention sometimes concepts that you might not yet fully know or understand. The random, first of all, it's always a good idea first to look at the type signature without without the part in front of the double arrow, right? So it takes a pair of 2 things. A pair type is really just a parameterized type, which is a single constructor data type that has 2 components only that's parameterized over the 2 components. So the first component is an A and the second component is also an A, right? And it produces a structure of A's, a parameterized data type of A's. And now there are two constraints. One constraint is that A has to be in the random class. And that's basically conceptually a class that contains all the types for which Haskell knows how to create random values of, right? It can create random integers, it can perhaps create random characters, perhaps it can even create random strings or something like that, right? In principle, you can extend, like usually you could make other types instances of the random class, but it's not derivable or anything. You would really have to do something in order to explain, here is how you can generate random values of this new data type. But in particular, integers are in the random class. And monad IO, for the time being, we can just assume in particular IO is an instance of this type. So the type signature we want, the instantiated type signature, we can look at this now at is this one, right? So we pass it a pair of integers, we get an IO int out. So if we try this, for example, we can do something like a roll with a 6-sided die. We can give a type IO int, and we can say that's a call to random RIO of 1 and 6. Okay. This is now of type IO int because we have applied it to its argument, and we get an IO int out. So this is fundamentally different from an int, right? Let me just repeat that again, because an int, if we have something which is of type int, then it is one clearly defined int, and it's always going to be that int. It can be 0, or it can be 42, or it can be whatever you like, but you choose it once, and then that's it. That's its value. But this thing is an action. I typically call these things IO actions, and an IO action is a description of something that if you execute it, it will do something and eventually result in an int. So how do you execute actions? The real answer to that is, if you write an actual Haskell application, then a little bit like with C or with Java or with many other language programs, there's one designated entry point to your entire program, right? You typically in a program have multiple modules, and there is one designated module which is supposed to be called main, and that designated module that is supposed to be called main should have a definition for an identifier which is supposed to be called main, and the type of that identifier is supposed to be an IO action. And that is the IO action that is your program, right? Everything that is that's typically a very complicated IO action that calls lots of other things and composes lots of other things together. But that is the IO action that will be executed by your program. But also, if you enter an IO action into GHCi or into the eval program prompt, eval plugin prompt, it will also execute that action, right? So that's the other way of doing it. We can just type something of IO in here, but the behavior is, strictly speaking, slightly different than before, because we now get a random number, and if I do refresh, oh well, in this case, I'll actually got three times 3 in a row, but now like the 4th time I got a 5, so you don't always get the same thing, right? And that is very different to everything that we've seen before, where the things were entirely deterministic. So if you put something of IO type into GHCi or the eval plugin prompt, it will execute the action and print the result, and it can do more things. And we'll see that this also very quickly reaches the limits of the eval plugin, because as long as you're only printing things, that's fine. But as soon as you have, for example, some input or user input or something, then the eval plugin won't be able to handle it anymore. So it's not not that useful for IO actions. You should sooner or later then switch to GHCi or actually compile full programs. But GHCi is typically fine. Okay, so that's a single IO action. But how do we roll 2 dice, for example? What if we want to do this twice? And not just like by running the program twice, but within one program, how do we do this? And for example, like we want to roll 2 dice and add up the results, similar to the example that we had before, right? Perhaps we want to write both these programs, like roll 1 die and add the result to itself, versus roll 2 dice and add the results of these 2. How do we do that? The answer to that is there is a sequencing operator for I/O actions, and the sequencing operator is this famous bind operator. We're famous because it's part of the Haskell logo, right? That's the reason that the Haskell logo looks like it does. It's a combination of the bind operator and a lambda. The type of the bind operator, I'm going to show the instantiated one. The general one is again more complicated, so I'll not actually ask what it is for the time being. I'll immediately instantiate it so that we have a slightly easier time understanding what it does. It's this. This is an operator that is intended to sequence, to build a larger I/O action out of 2 smaller I/O actions. And this is the first I/O action. And this is conceptually speaking the second I/O action. And this is the resulting I/O action. So the first one, I guess, is clear. That's just an I/O action that can produce some result of type A. And now the second one is not simply another I/O action, but it is actually a function that can use the result of the first I/O action in order to determine what you want to do next, right? Because you could imagine that you want to write a program that says, oh yeah, let's roll a die, and then if the result of the die roll is 0, I'm going to stop. But if it's anything else, I'm going to roll another die and do yet something different, right? And if you want to write programs like that, you need access to the results of I/O actions. And this is the one single fundamental way in which you get access to the results of I/O actions. It all goes back to this bind. There are lots of other functions that are defined on top of this. You're not always going to use this one explicitly, but this is the fundamental sequencing operator that allows you to build larger I/O actions out of smaller ones. Okay? And then you, because you have then full control, you can use the result to do whatever you want next. You return the result of the second one. But because that one had the first result available, that's not really lossy because, I mean, you can include the result of the first one in the result of the second one because you have full freedom what kind of function you want to put here. So let's just try this, right? I know this is very difficult on the second day of Haskell, effectively. Roll twice and sum. So the idea here is we roll twice with a die and sum up the 2 results, the 2 different, potentially different results. This is still going to be an I/O int. And this is going to be an application of bind. And the first action is going to be roll. Okay? Hopefully that is not surprising. And now what we have to do is we have to write a function that gets the result of the first roll and then gives us another I/O action of type I/O int. So the function, this is another place where lambda terms are really useful, or lambda expressions, right? It's another higher order function, and yeah, I mean, so we can just like write a lambda here and say, well, let's call the result of the first roll R1. And then we have that R1 of type int and scope, and we have to produce another I/O action. So after we rolled once, I've already said, what do we want to do next? Roll again, yeah? So we call roll again. But that's not the last thing we're going to do. Right? Because we still have to add them up. So actually we're going to apply bind again. I can already hint at that, right? And so, but the next thing is we're going to roll again. And Now again, we have to produce a function which goes from int to ioint. And again, we can give a result to the second roll. And now again, we have to produce an ioint. And now we need one more ingredient to make the system basically complete. All the rest is then just abstractions built on top of this. And this ingredient is that we want to add up the two results. That's really what we want to do. But if we now write R1 plus R2 here, that doesn't have the right type, because we're adding two integers. The result of adding two integers is an integer, but we want an IO integer. And now it's extremely important to realize that the relation between int and ioint, Tom mentioned this morning as well, is complicated. One direction is trivial, right? Every int can be lifted to be an ioint. That's very simple, because the idea of ioint is it's a description of an action that when you execute it does something and eventually returns an int. This action can obviously be one that does in fact nothing and still returns that int. That is very trivial. And so there is a function which is called pure, which is of type A to IOA, which allows you to lift any value and pretend that it is an IO action that always returns that value. And that is the one that we want to use here. The other direction, IOA to A, is strictly speaking impossible. It does not really exist. And practice will not lie to you, it does exist. There is unsafe perform IO in the library, also a very infamous function, right? But it should not be used, right? Period, right? I mean, there are very, very few use cases for it, primarily ones where you can argue from the outside that some encapsulated code does not, in fact, produce any observable non-determinism or side effects on the inside. But it's very, very rare. In particular, if you're not writing something which is close to the hardware or interfacing with other languages or something like that. But it's very, very rare. Don't look for unsafe perform IO. If you want to get out of IO, the answer is you can't. Because like as soon as you actually say you may depend on anything outside, external, whatever, you do depend on it. And you can combine it with other things, but the whole thing still depends on it. That's a dependency you can never get rid of. The way you in practice do this is using this trick, right? What you typically usually want is you want to work with the result of a previous action, and that you can do by using bind. You use bind in order to get access to a previous result, which you can then use in order to determine what you do next. But the end result is an IO action again. And that is why this is sound to do it in this way. Whereas if we simply would expose a function of type IOA to A, it would not be sound. So this is how you write in the fundamental and the most fundamental form, roll twice and sum. So if we try this out, roll twice and sum, we should get something which gives us a number between 2 and 12. Right, with a slightly bias towards the middle, towards 7. And 2 and 12 itself should be relatively rare. Right, but yeah, that seems to be working correctly. And you can in particular see you get odd numbers, right? We really roll twice because you couldn't get an odd number if you would only roll once and add the result to itself. And that's in fact what we want to write next, right? Roll once and double, just to put these two next to each other. How would we write this one? It's actually simpler than the other one. How do we write this one? We roll, and then we bind, and then we get one result. And then what now? Yeah, what exactly? I mean, you're right, like on a superficial level, but what? Pure, exactly, pure of what?
To multiply by R or
Yeah, r plus r or 2 multiplied by r both works, right? Yeah, but yeah, something like that, okay? And if we do that, roll once and double, we get only ever even numbers, right? And we get 2 and 12 correspondingly more often than in the other one, but that is a bit harder to observe. But yeah, it's, this is the one. Right, so this is the basic way to construct I/O actions, right? And now, based on these ingredients, on bind and pure, and some primitive I/O actions, if you like random RIO, which we used from the library, we can build everything else we want just using the constructs we already have in the language. Pattern matching, recursion, whatnot, right? Other helper functions and so on. There's one major syntactic thing which Tom also mentioned, of course, and which you probably also have seen already, which makes this more convenient in practice, and that is do notation, right? Haskell has yet again a special syntax for expressions written using binds that makes this a little bit more convenient, and most people would use do notation. So the way that you typically write roll twice and sum is you write do. Often this is written using sort of a hanging do, although I'm not the biggest fan, and then you indent the next line. And then basically, as a first step, you can basically just rearrange the lines here. You can say, like, look, I mean, really, this whole function from here to the very end is the second argument to the first bind. But nevertheless, it's also the case that R1 is the result of this roll. So let's make that association more prominent by inserting a line break right here. I'm not doing anything but inserting a line break. And then similarly, R2 is the result of this roll. So let's insert another line break right here. Right? And that's the same expression as we had before. And now the way that do notation corresponds to the sequence using binds is simply that you flip the order around and use a left arrow. So you write R1 left arrow roll, R2 left arrow roll, and then pure R1 plus R2. And that's the way that most people write this. But it means exactly the same as that. Yeah? Okay. The question is, what is return?
No, I thought it was return and not pure.
You thought, yeah, the remark is, I thought it was return and not pure. You can write return as well. So this is a historical thing, and return is perfectly fine. The situation is this, then when all this stuff was first introduced in Haskell, then it was with return and with bind. Then later, an additional variant of the underlying abstraction, which is a monad, was invented or discovered in the context of Haskell. It was introduced, which is applicative. And applicative comes with a method called pure. And pure and return are supposed to be always the same. I mean, two different structures, but the implementation of pure and the implementation of return is supposed to be always the same. And these days, that is even kind of enforced in the sense that if you are giving an implementation of return that is different from the implementation of pure, the compiler warns you about it and says you're using a non-canonical instance and so on and so forth. And some people have therefore argued that the presence of return is in principle superfluous these days, and you could just remove it from the libraries. And it's slightly more fashionable these days, I would say, to use pure than return. I like it better primarily because return always has this operational thing. Perhaps that's no longer that much of an issue, but in many other languages, return is being used to signal you abort the execution at this point, where you, like if you have it in the middle of a block, right? You don't continue past the point of where you have the return, you actually jump out of that function. It doesn't do that in Haskell. You can do stuff after the pure here, then the result of the pure will be ignored in principle because you're not performing any effects and you're not using it. But does go on past that point. So in that sense, return as a name is sometimes a little bit misleading because it doesn't actually return. The only property it has is that it is most often used at the very end of such a sequence of actions. But in principle, yeah, the two names are interchangeable. If I would put return here, it would equally work. And if you look at the actual types of these, then the type of bind is the one that I've given to you, except that it is generalized over the monad class. So the sort of incomplete explanation of monads is simply monads is this interface that is given through return or pure and bind through these two things. And there happen to be, and that's one of the cool things, many other types that also implement this interface, that also have a sequencing operation that works much like this, and also have an embedding operation that works much like this. And so you can use do notation and the same concepts and the same abstractions for all of these, and that makes it very nice. But for the time being, you can always think I/O when you see monad, right? You can just pretend this is IOA to AO, IOB to IOB, and then if you look at what is the type of return, you'll see that that's monad M, A to M of A, and then if you look what is the type of pure, that is, as I said, the same as the type of return, except that it uses yet a different type class, which is applicative, which is slightly more, depending from which direction you look at it, slightly more general or slightly more restrictive. I mean, slightly different than a monad, but nevertheless very similar. But again, all you have to know for the time being is that I/O is an instance. Yeah.
Just a question for the general understanding. Like, if
yeah.
I introduce I/O, like it's a side effect into my program, I cannot get rid of that in any way. So I always have to like carry through that dependency or that side effect.
Yeah, that sounds very frustrating at the moment, but the point is you like, first of all, you can temporarily get out, right? And if you like often, right? Often, what is the way in which you do I/O? Let's think of, say you have a web server, right? The web server listens on some connection for an incoming request. That is a very networky I/O-like action. So obviously that will be an I/O, and you will get some whatever byte string, like on the lowest level, right? You'll get some sequence of stuff out of that request. And in the end, you'll want to send a response, and that will expect a byte string or something like that as an input at the same lowest level, and is also a very networky I/O action. But what you're doing in between, as a first approximation, could be entirely pure, right? So you have, like, then on the lowest level, you have bytes. You have to somehow, between these 2 points at the end, you have to write a relatively complicated thing, which is byte string representing the request to byte string representing the result. But you can do that potentially without any further I/O, and you can write that in your code without using anything, right? So you write a decoder from byte strings to a more informative request type. Then you write a router that decides, depending on which kinds of requests you want to call which other kinds of your program. You write the other kinds of your program that deal with the contents of the request in a particular way and produce typed results. And then you write an encoder that encodes it all back to byte strings again. And all that doesn't necessarily need I/O. Perhaps at some point you discover that, oh, well, no, actually I also need something from a database, and that is again an I/O-ish action. But again, that just adds one additional step that you need to do sometime early on, perhaps, where you need to say, oh, well, depending on this request type, I actually need to run one other I/O action which fetches all the data I need, but then the data you need lives in the pure Haskell world again, and then again the whole rest of your logic can still be a pure function. So it's not that bad. I mean, I think it encourages a style of separating things that actually do side effects from things that don't more than you would usually do. But that is actually typically leading to cleaner code. I mean, I'm obviously convinced, and you don't have to be, but I think it is actually great that it is this way. Yeah. But I can fully understand that it seems incredibly scary initially, but it turns out to be working quite well. Yeah.
Maybe one question. So taking this database example, I want to get some data from the database, then I have, let's say, just an integer, so I have an IO int.
Yeah.
And then I have some pure calculation that I want to do this. So how do I do that? Because then I want to, let's say, very simple calculation int to int.
Yeah.
But from the database, I get this IO int.
Yeah.
So how do I insert the IO?
The question is, if I get an IO int from the database and I want to do a pure calculation on top of that, how do I do that? The answer is basically always bind, right? I mean, you run the action, or you basically build an action that first does your database query, which is an IO int. Then you have the opportunity to put a continuation action in that takes a plain int, and this can call other functions that just take ints to ints, right? Like that, and then in the end you have to wrap it in something again which is IO, but it can happen very, very late in the process, and there can be lots of stuff you do in between, which is just from ints to ints.
Okay, no,
Yeah.
I'm missing this wrapping IO step, yeah.
Yes?
So what if I have to, like, what if I want to roll 3 times and then return the sum of the first 2 and the product of the second and third?
Okay, yeah, that's good. That's good. Yeah. What if you want to roll 3 times and return the sum of the first 2 and the product of the second and third? Yeah. Okay, let's just do that. I mean, shall we use do notation or binds explicitly? What is better? Do notation. Okay. Yeah. Roll thrice and do stuff. I'll call that. Okay. And you said you want to actually return 2 integers in the end, so I'll perhaps return a pair of 2 integers, okay? Okay, so we do. We roll once, call the result R1. We roll twice and another time and call the result R2. We roll yet another time and call the result R3. And then we are doing pure, and what was it? Sum of the first 2, product of the second and third. I mean, so this is, you can also define your own type, right? I mean, it depends on what you want to do with it. So you can also my data stuff, right, to stay in the theme, make stuff contains 2 ints. That's also fine. Then and deriving show perhaps. I mean, then we're back to this. Then it doesn't have to be a pair. It can be a domain-specific type that contains these 2 ints that you have defined somewhere. Then you would write it like this, but it doesn't change very much, right? I mean, any type that somehow, or you could also call any other function that needs these 2 ints as an input. It's just, yeah, the only thing that is important is that you explicitly say for each of the fundamental actions in this case, how do you call the results? Okay, so yeah, so actually, I mean, this leads nicely into a follow-up question that I would have asked. What if we want to roll n times? Right? What, I mean, like we've now seen like 1 time, twice, 3 times, but it's getting a little bit weird. I mean, like, do you really, if I want to roll 100 times a die, do I really want to write a do block that has I mean, no, we're programmers, we want to abstract, right? I mean, so obviously we should still be able to write functions that do interesting stuff. So let's try to actually be immediately ambitious, perhaps, and just write a function times that takes an int and takes an IO action. And what would be a good result type? Like the idea is we want to, this could be like our role, right? I mean, we want to do this action actually in sequence this many times, right? If we like pass 10 here, we want to roll 10 times and then somehow get the 10 results out of that. So what would be a good result type for this function? So we have I think two slightly different answers. Is actually excellent that we have both these options. So the one suggestion was, I think, list of IO of something, and the other suggestion was IO of something. Did I hear that right? List of something. Yeah. Okay. Great. Yeah. I mean, so actually, I would say both are correct. They're slightly different, and one is in the end slightly more useful, but the other is a useful intermediate step. So, in a way, so let's see what this is, right? So this is a list of IO actions, and the good thing about this one is we know, well, it's very easy to generate that one. I mean, like very easy to write this. Let's actually call this 1 times 1 and this 1 times. I think times 1 is easier to write. How would I write times 1? We haven't really done a lot of recursion based on integers. And the problem with integers is actually that Haskell doesn't, unfortunately, have a good natural number type, not one that is widely used. But I mean, really what you want here is to never see a negative number, right? So the way this is typically done is that you're using a guard, and most of the time people are then basically just saying if this is equal or smaller than 0, then we do some base case, and otherwise we're doing something different. So what if I is 0 or negative? Then, okay, we also get an action, right? But it doesn't even really matter that this is an action, as we shall see. We produce the empty list, right? If we want to repeat this 0 times, then we produce the empty list. And otherwise, we want to do it at least once, so we produce a list which contains the action, and then we do times 1 I minus 1 of action, okay? So this function does not do anything specific to I/O. The fact that I've been writing IOA here and action here and list of IO here is a complete accident, so to speak. If I ask the type inferencer and comment out this code for the time being, what the type of this is, we'll actually get something which is far more general, right? I mean, I don't even want it to be that general because I am prepared that this is actually just an int, right? I mean, it can be anything that is numeric and ordered is what is being said here, but I'm okay that T1 is an int. But the other is really unconstrained. It's really can be anything into A to list of A. And this is actually a function that exists. We've just written yet another standard library function. It exists even in the prelude. This function is called replicate, right? And replicate just repeats an element in a list a number of times. Replicate 5 of 3 gives you a list with 5 times 3 in it. Or replicate 10 of the character x gives you the string that contains 10 x's, right? So this is a very useful function, and times 1 does exactly the same thing, and it's cool. It also works on I/O actions and gives you back a list of I/O actions. It totally works. The fact is, though, a list of I/O actions is not an I/O action. It's a list. And if you actually want to run it in the end, you need a single I/O action. So you still have something left to do. You need to take a list of I/O actions into a single I/O action. And rather than implement times 2 directly, which you also can, given that we've now written this one, we can actually try to write the other one. And let's call that in sequence. In fact, I mean, that one is called sequence in the library. It also exists. And the type of in sequence is then list of IOA to IO list of A. The idea of in sequence is you get a list of IO actions, and you simply want to connect them all, right? Like do one after the other, pick up all the results, and return all the results in a single list. So standard design principle, if it's the empty list of IO action, we have to do one thing. If it's an action followed by more actions, we have to do another thing, and we probably want to call in sequence on the rest of the actions somewhere in this. This one is, I mean, it's not entirely simple. It's not as simple as the other base cases, perhaps, but it should be doable, right? What do we have to do here? We have to produce an IO action that produces an empty list. Pure empty list, exactly. And here, yeah, okay, so we want to use bind. I mean, that is relatively clear, right? Because we want to do multiple things, or we use a do block again, but that's the same thing, really. And what we want to do first is we want to do action. Right? That's the very first thing that we want to do, because it's the first of our actions. And that action has a result, and we can call that R. And then we want to do this recursive call, and that gives us another action. So if we like have in-sequence actions, that is an IO of list of A, recursively, right? And that gives us another result, which is already a list. So we can call the result of this in-sequence action recursive call RS. And then we have to still produce an IO of list of A. But now we have two results. One which is the result of the first action, and one which is the list that comes out of the recursive call. And so what do we have to produce here? Yes, wow, great, fantastic. Exactly right, okay. Yeah, and now we can write times 2 as a combination of these two functions. So if we want to do I times action, we can first call times 1, or let's actually give the better names, replicate of I of action. And then we have a list of IO actions, and we call sequence or in sequence on the result of that. And then we have what we actually want, right? So yeah, let's perhaps actually call this one my replicate in order to just make it slightly easier to remember the real names of these in the library. And this one my sequence rather than in sequence, because it's called sequence in the libraries. And the combination actually also has a name in the libraries. This one is called, so here I can call the actual sequence as well. This one is called replicate M, my replicate M with a capital M for monad. It's a sort of like an IOified or monadified version of replicate, right? Replicate and then sequence. And my replicate let's try that. My replicate M, if we do 10 rolls of the dice, we get a list of 10 random numbers between 1 and 6, right? Or if I do 20, I get this. And I can put any other IO action there, like, I mean, like the roll thrice and do stuff. I can do that one 20 times. Then I'll get lots of these results, right? And this, I think, is a glimpse. I mean, we are nearing the end of time and we won't be able to do very much more, but it's nevertheless a good glimpse that there is, I think, a nice story about the interaction of I/O actions and functional programming. Because, like, at first you might think that, oh, well, the introduction of these do things makes everything imperative again. But if you keep the different aspects that already came up in the questions in mind, like the first thing that came up a couple of times, yeah, sure, at some point you'll have I/O actions, but even though you'll have I/O actions and that will sort of in the temporal sense infect everything, it doesn't actually in practice infect everything, because you can still extract results from some computations, write functions that work on these results, and entirely pure functions that work on these results, and then re-inject them somehow into the overall I/O action. So you can separate these things out. But also, you can write lots of sort of high-level functions, such as replicate M or traversal operators or things like that, that just do interesting stuff with I/O actions, right? Another interesting one, for example, is that you can do a monadic version of map, right? We've seen map earlier today, and there is also a map M, which goes from A to I/O, and I'll give let me call this my map M again. I'm going to give the specialized version here as well. Has a list of I/O A, a list of A, and then gives you an I/O of list of B. So the main difference between my map M and map is that this is an I/O function, a function that produces an I/O action, and the result is a single I/O action. So the idea is you're running the I/O action, the parameterized I/O action, with all the inputs from the list, and you're doing all the resulting actions in sequence, right? And then you're collecting all the results again. So again, this is actually written as map F of XS, which again gives you a list of I/O actions, and then again calling sequence on the result. So it's nothing more than that. And then my map M, for example, on simply, let's say, random RIO, you can do this like on a list of pairs of integers, right? You can say, I want a random number between 1 and 5, and then another one between 2 and 6, and then another one between 4 and 22, and then one between 1,000 and 2,000. And let's leave it at that for the time being. And then you get those 4 random numbers out, right? Yeah. Any questions about this up to this point? I think we are at the end of the official time. Let's first ask whether there are any questions, and then perhaps I have a small suggestion. But no? So what I was originally planning to do is to write a simple interactive guessing game. So what's the idea of that? It would have been to not really introduce anything on top of that except a few additional primitive I/O actions, namely, these are definitely still useful to know, and that will only take me a moment to introduce. They also already featured in the talk today. Put string line is very useful. So what is put string line? Put string line is taking a string and producing an I/O action that when executed prints that string. It doesn't have any real result. So this unit type, I mentioned it in the exercises of day 1, but I didn't mention it in the lecture yesterday. The unit type is a special data type which you can look at as a data type that has only a single value, which is also written like this, and is also pronounced unit. And it is often being used as a parameter for something where you're not actually interested in it, right? I mean, so in this case, we have an I/O action that produces always the same result, essentially, and that result is called unit, because with putString line, we're not interested in the result, we're only interested in the effect, right? And then there is the counterpart is getLine. And getLine is an I/O action that produces a string. And when getLine is executed, you'll actually read a line from the user keyboard as input. And when the user hits return, that string that the user entered is going to be the result of the I/O action. Right? And with putString line and with getLine, you can program interactions. And in particular, you can implement some loopy stuff. And the idea that I had was to simply write basically a game, in quotes, because, I mean, it's a trivial game, that has a state where initially you generate a random number, right, just as we did, and that is kind of the secret. And then perhaps you have a counter of how many guesses you have had. And so basically you define your own user-defined game state data type that contains this counter and this secret. And then every time you enter the function, you ask the user to make a guess, right? Using getLine, I mean putString line, send a message, getLine, ask the user to make a guess. Try to interpret the guess as an integer, compare the guess to the secret. If the guess is correct, you say you won and you stop. Otherwise, you say whether your guess was too large or too small. Then you update, effectively, you produce a new state data type where you increase the round counter by 1. Then you call the function again with the updated state. And that's it. That is the game, right? Of course, we still have to write it. We have two options, I think. One option is I'll just leave it at that, and that's almost my suggestion, because I think 2 hours in a row are already quite a lot. And you're welcome to try this as an exercise. All right, there are also additional exercises still in day 2 exercises, but they are not spelled out. They're essentially just links to my main course, which contain similar questions on this level as well. In particular, assignments E contains a number of small exercises, and optional assignments X contains essentially an implementation of, in several little steps of a game which I think I know under the name of Mastermind, which is also a guessing game, but you have a secret which is a sequence of colors, and somebody else has to basically guess the right sequence, and you always get some hints about how correct or incorrect your guess was, and you have to, that's actually interesting in the sense that you have to apply actual reasoning in order to interpret the hints that you're getting in order to get closer to the secret. And I think that's entirely doable with what we've talked about today. So yeah, it would basically be my suggestion that you just do that in the exercises, and I'll still be a bit around, and if you don't want to do it, that's of course also fine. But I am also offering to still do it live if there are many of you interested, and we can either do it on the recording or off the recording if you have to stop it because you have to get away. I don't know. Yeah. So who is in favor of just doing it as an exercise? Okay. And who is in favor of doing it live? That's fewer. Okay, good. That's very clear. Then that's it. Thank you very much. Hope you enjoyed it. If you have any more questions, then we'll still be here. Joris is also here. Matthias is also here. Yeah. Okay, thank you.